Good morning, and great to have you here. Welcome to the third annual virtual symposium for the Houston Methodist Institute for Robotics, Imaging and Navigation. Now we're here streaming live from the DeBakey CV Education Studios here at Houston Methodist Hospital in the Texas Medical Center. And I'm your host, Dr. Stuart Corr, Director of Innovation Engineering. Now, you can see from my first slide here, over the next 5 hours, we will be learning from key figures in the fields of robotic-assisted surgery, extended reality, and spatial computing. And we're understanding more about the interplay and convergence between them. Here's a little snapshot of the agenda. In the first session, themed robotics, clinical and research updates, we will have representatives from national and international institutes such as the Hamlyn Center, Boston University, Stanford, and Houston Methodist Hospital. In the second session, we will be taking a peek into new industrial innovation and tech developments across in the fields of virtual and augmented reality and spatial computing, with presentations and thoughts from Verizon, Methodist, Avatar Medical, Level X, MediView, Biomed, and Fundamental VR. And now, if you want to get the full agenda, please click on the link in the description on YouTube. It's mirren23.info, and that would take you to a registration site which is free, but it will give you access to the agenda. Now, a quick snapshot, quick overview and history of Mirren, should I say, the Houston Methodist Institute for Robotics, Imaging and Navigation. So a couple of years ago, we decided, hey, we've pretty much got every single FDA-approved robotic system, imaging system available. However, there's always the perennial siloing effect. We want to break down that and pull together all our surgical staff, all the physicians, etc., and start seeing what toolkits they're using, start understanding what problems they're facing, and use that as a new platform for innovation, research, and development. So thus, Mirren was born. And now one of our missions is to develop and integrate robotic imaging and navigation technology into the hospital, but to allow for enhanced and precise patient care. And we try and do this through our key results, which are measured in the themes of image-guided robotics, extended reality, spatial computing, artificial intelligence and digital surgery, and training and education. Now, if you look on the right-hand side here, this is actually going to be a nice segue into our first special guest. It's Professor Ferdinando Rodriguez. He's the co-director for the Hamlyn Center in Imperial College London. And we could think of no better institute to try and emulate and try and partner with and see what they're doing than the Hamlyn Center for Robotics. So I'm absolutely delighted to have on the show Professor Ferdinando Rodriguez, who is streaming in live from London. Ferdinando, welcome to the show.
Thank you, Stuart, and thank you everyone for having me. It is an absolute honor to join this symposium. And in fact, we tried last year, and then a personal circumstance that was urgent meant that I couldn't make it. So I'm delighted to be here today. I need to share my slides, which I should be able to do.
And while you're doing that, just to let the viewers know, myself and Dr. Anna Lumsden were able to go over to London this year to the Hamlyn Symposium, which I highly recommend people go to. It was absolutely fantastic, and we got to meet Ferdinando face-to-face and tour his facility. So, what is the secret sauce, Ferdinando? How do you run an internationally acclaimed robotic institute? Please tell us.
Well. I wish there was a secret recipe. I think it's a little bit bespoke, and there's a little bit of luck that goes in it. But hopefully, at least through sharing our experience, we can give some of our audience food for thought. Needless to say, I am a professor of medical robotics to start with. So I am a professor in the Department of Mechanical Engineering, but took on the co-directorship of the Hamlyn Center about 3.5 years ago. And that was a privilege and a fairly daunting task because, of course, I didn't create the center. I had the privilege to jump on board and try to reshape it for the 21st century. So it is fair to say that within the context of healthcare and healthcare robotics, Imperial has quite a little bit going on. There is work inside and outside the operating theater, ranging from human augmentation to surgical robotics, working with cerebral palsy children and for the elderly and so on. And within this context, the Hamlyn Center is basically there sitting across the two faculties of medicine and engineering with dedicated space across 3 campuses to really try to bring some of that expertise together for the benefit of clinicians. So if there is one particular focus for the center, is not only doing incredible science and engineering, but also trying to target some of that science and engineering towards the solution of clinically relevant problems. And I think through co-locations and this co-directorship with a clinical director and an engineering director, we're trying to build that bridge across an institution that does very well on both of these aspects. Now, if you look at the makeup of the Hamlyn Center, it's got 3 main prongs. And I think over the past few years, we've tried to fine-tune how the balance of these 3 aspects of our strategy fit together. First, the center is an opportunity to bring state-of-the-art equipment together under one roof, trying to give each piece of equipment and each facility enough of a footprint and enough of a user base in order for it to be sustainable long-term. We all know that equipment is expensive to buy, is even more expensive to run, and it has a sell-by date. So one of the ideas behind the Hamlyn Center is to be able to share all of this in such a way that it can be fully utilized, not only by those who sit within the Hamlyn Center, but also for those that are outside the Hamlyn Center. Secondly, it's a teaching space. So we run a fairly successful MRes in surgical technology, and that is run through the Department of Surgery and Cancer, which is the department within Imperial College Medicine faculty that hosts half of the Hamlyn Center. And of course, it's targeted at making the most out of the academic taught program that our academic base can deliver. But we also do things, as Stuart said, which are a little bit more bespoke. We have a winter school just before Christmas. And then, of course, our flagship symposium once a year, which I would absolutely encourage you to come to if you wanted to have a flavor of some of the best surgical, robotics, and allied technology space from keynote speakers worldwide. Finally, and I think that's the differentiator, while we do fundamental research in imaging, sensing, and robotics, it is fair to say that we do spend a large amount of our time trying to build the bridge between bench and bedside, which is not easy, especially in the medical device space. And we're trying through training in entrepreneurship and medical device development and certification, and by creating an environment where clinicians and engineers work together to accelerate that process in as much as it is possible. Now, as I said, and I think this is the focus, as an academic at Imperial, I have these sort of 2 hats. I am the co-director of the center, which I'll be very happy to talk about more, but I'm also a professor of medical robotics. And in this context, I have spent the past 20 years developing technology for predominantly surgery, but also with work in training and diagnostics. And so I wanted to take you through a little bit of my journey through medical robotics, and then share with you some of the lessons that I learned and some of the latest things that we're doing now, which are hopefully a little bit closer to market, which basically means also closer to affecting our intended audience, which is patients. Now, if you look at the landscape of surgical robotics today, it is mighty different from what it was 20 years ago. Yeah, so 20 years ago, it was cowboy scientists and clinicians bringing this sort of very green technology to the operating theater with, let's say, a regulatory framework that would not stand scrutiny if you looked at it with the eyes of someone in 2023. But at the time, it was sort of exploring technology and its potential use within the operating theater, which is the closest thing to a war zone, yeah, in peace times that I have seen. It is very difficult to make things fit, yeah, what the space of an operating theater is like. But today, things are very different. So what you see on screen are a number of robots that actually stood the test of time and are now commercially available, but not only. They are no longer small fledgling companies without a turnover. They've all been acquired by large corporations like Medtronic, Stryker, Zimmer Biomet, and so on, who have the weight of the income that is generated by other medical devices to finally bring surgical robots to the forefront. Now, our own history in surgical robotics, as I said, is now fairly dated, but it helps to paint the picture of how far we've come from the sort of the green days of the late 90s and the early 2000s. Because the robot that I have direct experience of bringing from bed to bedside is one called Acrobot. It was used for orthopedic joint replacement, and it was unique at the time because it was the world's first robot that used this idea of cooperative control, so robot and surgeon working together in pursuit of better targets. It is a very dated video. In fact, I'm going to run it, right, where we've got our then surgical registrar and a very close friend of mine whose name is Johan Henkel, an orthopod, who worked with me to try to get this system to patients alongside a team of much more experienced researchers and scientists than I was, that basically allows the human to paint the bone in a joint replacement freehand with the robot, with the motors of the robot engaging to prevent you from cutting where you shouldn't be cutting, right? And that was the first step towards this idea that you wouldn't either have the robot in command or the surgeon in command, but actually robot and surgeon working quite closely to one another. In the early 2000s, this was sort of almost, well, it was beyond the state of the art. Well, now it's sort of expected because things have moved on quite a lot. As you saw, as you can see here on the right-hand side, it was born out of a research project. It became a spin-out company of Imperial College called Acrobot, and then went through a number of acquisitions. So at least the soul of Acrobot is now probably behind the Mako systems of Stryker, which is now one of the mainstream robotic systems in orthopedic surgery. Now, back then, we demonstrated conclusively that a robot could perform better in terms of accuracy and repeatability through a small, focused clinical study where we compared clinicians using conventional tools and clinicians using the robot. So without any complicated statistics, if you think that gray is the position of the implant as you had planned it, and yellow is the position of the implant as you had put it, you can see that the amount of difference between yellow and gray on the left-hand side, which is human beings doing their best with jigs and fixtures, is significantly broader than on the right. And so this work, which was quite a landmark piece of work for us in Imperial College and has been replicated and exceeded 10 times over since 2006, demonstrated conclusively that robots were more accurate, which begs the question as to if back in 2006, robots were unequivocally more accurate and precise, why are they not mainstream today? And unfortunately, the reasons for this are multiple and they are quite nuanced. Some have to do with clinical workflows and patient acceptance. Some have to do with the purpose that robots fit in the operating theater. Now, for the former, I mean, the work that is required is many, many more clinical trials, or RCTs, with clinicians and with healthcare providers, because finding the right placement of this technology within the clinical workflow is a rather complicated process. But as an engineer and a scientist, what I've been focusing on for a number of years in my own group is to think of the technological opportunities to make these robotic systems a little bit more accessible. And if we look at the landscape on where the limits of current technology are, I personally think that the future should revolve around three main areas of improvement. Smooth interactions, so try to make the relationship between the robot, I would call it between the surgeon and the technology more seamless and natural, right? Making sure, and this is automatic recognition, that there is no additional step that the technology forces upon the clinician. So the clinician should just focus on the job in hand, which is to help the patient, and the technology should, in a future not so distant, just come to the rescue of the clinician without any need for deviating from the standard. And finally, a new generation of devices that are smaller, cheaper, more dexterous, safer to use, and so on. So within this context, a very brief summary of some of our latest work. And I always start with this diagram because it highlights what technology in surgery is today. Because regardless of the robotic system or the brand, all systems today pretty much have these two main components to it. They've got a two-dimensional screen, same as they did in the 1980s, and they have for any type of surgery that involves the tracking of part of a human being, so for example, a limb, the insertion of percutaneous screw deep within the tissue, which basically means an additional stab wound, and it means additional risk of infection and so on. And so for the past few years, what we have tried to do is very much trying to overcome the limits of this technology with technology and software. Now, on the software side, I am an absolute believer, as Stuart is in Houston, that the future is AR and mixed reality, right? And that is because there must be a better way to deliver the right information at the right time without cluttering the operating field and without the surgeon having to triangulate in real time what they see on screen with what they see in front of them, which is the patient. And what you see on the bottom right-hand corner is some very recent work in collaboration with Smith & Nephew, the makers of one of the more successful robotic systems in orthopedics called DeBakey, where we take the information from the screen and we overlay it directly within the view of the surgeon through a Microsoft HoloLens machine. Now, clearly, this is proof of concept because the HoloLens has not been designed for this type of application. And so the accuracy and the speed with which we can perform the rendering is limited. But you can see from the video in the bottom right-hand corner that by delivering information about what points you're touching or what part of the bone you have to cut directly on the plastic bone here, you can have a much more ergonomic and facilitated view of the type of assistance the robot can provide the surgeon. And I think it is a great little window into I think the future of this technology. Now, if this is how you display it, yeah, there is a very big thing about how to track things, right? And the process of registration has for decades been the mechanism by which you align the space in which you plan the surgery and execute it with a robot with the space of the surgeon and the patient. Now, what you see on screen here is our work on trying to use robotics and depth imaging, so cameras that take three-dimensional views of the scene, to try to automate that process of tracking where the patient is. So you've got a camera mounted on a robot, and the robot does three things. It keeps line of sight of the limb being operated upon. It can be manipulated interactively by the surgeon. And of course, it reconfigures if there is an obstacle that comes in the way of the patient and the camera. Now, you'd be right to say that in a setup, as you see on screen, the difficulty is much simplified because you've got a clean laboratory space and a plastic bone that you're trying to track. And so, of course, our next step was to try and demonstrate that we could do this type of tracking, but in a much more nuanced and complicated environment, like, for example, an operating theater. Now, if we go back to what a camera sees, it is a sort of point cluster you see on screen here, right? It's only points. The system doesn't know anything about what these points represent. While we, as trained viewers, know that the bit of the point cloud that interests us is the bony part in the middle, and the one around it is not important to us. So what we tried to do for a number of years is teach a deep learning algorithm exactly how to make that discrimination automatically. And we did this by taking cadaveric limbs, which are different in their own right, placing them in a realistic environment under differing lighting conditions, and then semi-automatically teaching the algorithms what we were looking for, what is bone, what is cartilage, and what is not bone. And we did this very, very many times, sufficiently so to train a network to do the type of discrimination we do naturally, but without any user input. And so what you see in the videos here is our very first attempt at doing this automatic image segmentation. So what you see on the left is what the camera sees fresh, no pre-processing, no registration. And what you see on the right is the algorithm's ability to identify what is bone and what is not. And more recently, we can also do this, as you can see in the bottom, in the presence of occlusion. So we can robustly identify elements of tissue, even though it is partially obstructed by the hand of the surgeon. So not quite ready for prime time, but you can see the path that has been plotted, where you're bringing state-of-the-art imaging and algorithms and tracking in order to create a robotic system that is much more seamlessly integrated within the workflow of an operating theater. Now, I wanted to finish with a few examples about devices, because devices have gone through a significant evolution over the past 20 years. And I just picked 3 or 4 that are much closer to market than some of the fundamental work we're doing in soft robotics, where we're maybe 5, 10, or even 15 years away for anything being of clinical practical value. So an example here is work we're doing with the latest spin out of my original PhD supervisor, whose name is Brian Davis. His company is called Signature Robot Limited, where we're trying to look at the same concept of the Alaa robot, but with a much more compact handheld device. We have work here that was done in cooperation, in partnership with with De Sutter Medical, which is a British electric drill manufacturer who's now expanding in the robotic space. And here, we've been using the same technology that you use in a surgical robot, but to create patient-specific instruments that are done on the fly during the surgery itself. We don't really have time to look at it in great detail, but the machine that is now being industrially designed and is soon going through clinical trials is called Celito, and Prometheus is targeting shoulder replacement as one of the first clinical procedures to focus on. And then, of course, we've got work on minimal invasive and endoluminal surgery. And this is work that has been 5 or 6 years in the making, where we're taking best-in-class non-magnetic manufacture and actuation, so pneumatic and plastics, to create a robotic endovascular system. So as you can see here in the video, it's got a top end, so a patient side, which basically is used to insert endovascular catheters, for example, for pericardial ablation or for stenting. And on the bottom, you see the surgeon side, which is this sort of bespoke patented device that allows the clinician to insert the catheter very similarly to how they would do it in the conventional setup. And it is fair to say that this technology has been licensed to a company called Magnet. And my PhD supervisor, I was the supervisor, my PhD student Mohammed has now spearheading the engineering team within this company. So hopefully it also sees the light of day as a product. And finally, I cannot but finish with my baby. I have got 2 human babies, and I've got a technology that I started working on my first year as a lecturer, and it is a needle steering system for neurosurgical procedures. It was called Sting in the days of my early career, and it became Eden when I secured funding in the order of about 8.5 million euros to work with partners across Europe to create this platform technology for precision neurosurgery. Again, in a nutshell, it allows you to steer a flexible catheter around tight bends within very compliant tissue like brain to offer a number of diagnostic and therapeutic modalities directly at the business side. Now, the technology has gone through a very long journeys of up and downs, but it now looks like you see it on screen, especially with preclinical trials on the live ovine model, so the live sheep model, recently published in PLOS ONE. So where are we going next with this? Well, hopefully, maybe a spin-out company where the main ingredients of this technology can be put to use within the context of a commercial framework, which could tentatively be called Neoptra Surgical. The situation has been hampered by the main hit of the COVID pandemic and basically the repercussions thereof, but we're still working to see whether we can give this particular technology legs. So with that, I wanted to just end on an unequivocal high, in that over the 20-odd years of being a researcher, scientist, and academic and entrepreneur in this area, I couldn't think of a better time to be a medical roboticist. Software and hardware are reaching heights that I couldn't have dreamed of even 5 or 10 years ago. And I can only imagine what the next 5 or 10 years have to offer. With that, I'd like to obviously thank everybody in the team who does the work so that I can come and not embarrass myself. And of course, the funders that can pay for what is very expensive and long development processes for medical robots. And finally, to remind you that the Hamlyn Symposium is in June, and you're very welcome to join us in London. Dates are 25, 28 to see workshop, keynotes, and so on and so forth. So with that, I'd like to thank everybody, and I'm very happy to take questions. Stuart, back to you.
Thank you. I feel I need to give you a round of applause there. That was absolutely phenomenal, Ferdinando. Thank you very much. I've got a few questions here. So going back to the beginning, I guess. I know you said that you weren't there right at the inception part, but can you maybe comment on how they chose what research directions to take the Hamlyn Center in? Or was it really they were grouping what was already going on and put it under an umbrella organization?
So I would say that it's half and half, in the sense that the center, as it was born, was built upon the track record of my still co-director, Professor Delord Aradazi, who was really one of the clinical pioneers of medical robotics and, in fact, technology in surgery in the United Kingdom and probably worldwide. And obviously the then co-director, whose name is Guangzhong Yang, who was the founding co-director of the Hamlyn Center. Now, clearly, the original center was supported by the generous endowment of Lady Hamlyn and the Hamlyn Trust, which basically gave birth to the center as you now know it. Now, it's fair to say that pressures of funding bodies and priorities that come from the government and so on have now shaped the direction the Hamlyn Center have gone over the years.
Understood. And did you find along the way that you were bringing in, recruiting new research talent, like new areas of research that you weren't doing at the time, but you thought would be a good plug and play into the Hamlyn Center?
100%.
How did you approach that as well?
So in fact, I think we have a perfectly pertinent example. So our academic membership has now expanded by 2 over the course of 2023, with 2 academic appointments starting in September of this year, so just started. And one of the areas that, for example, we identified has enormous value, but we were light on with regards to academic leadership, is micro nanorobotics, which, if I have to be honest, is the most exciting but longer term technological challenge in the space of healthcare technology. Now, this is basically developing the sort of devices that I am familiar with in first person, but instead of a macro scale, at a miniature scale. So what is small for me is incredibly big for the space. So we're talking microns or nanometers, so working at a cellular level. And of course, for that, we had to strategically recruit academic leadership in the space, which hopefully will then now open up a new area of growth that goes well beyond what I could do in first person or anybody else here already.
Got it. And obviously 2023 has been a huge year for artificial intelligence. So do you guys have the infrastructure already to handle AI integration, or are you looking for that?
Yes, indeed. And in fact, it's an incredibly topical area for us as a community. And in fact, fair to say the focus area for Hamlyn Symposium next year, we have a theme every year, is in fact, as you see on screen, AI-driven health transforming care. Mm-hmm. It is ubiquitous. We cannot get away with it. Now, people like me use AI and machine learning as the latest in the range of instruments that you can do to solve a practical problem. And you saw the amazing result we showed with depth imaging and automatic segmentation, purely based on advancements that others have made in the architecture of these deep networks. We don't necessarily do the fundamental science, but pretty much every researcher in the center would have dabbled in machine learning in one way or another. It's important to say we have a significant early piece of work across the Institute of Global Health Innovation, because the main challenge we have as a community is to find the right regulatory environment and the right relationship between hospitals, companies, and academic institutes like Imperial College and others, to make the most out of the data that is integral to teaching these algorithms, right? So it is as topical as it comes, and we have early work in place that we're hoping will materialize in the not too distant future, which hopefully next time I can come and talk about in a little bit more detail.
Okay, and you hit on a really good point there that was going to bring up one of my questions, is what type of research are you more heavily involved with? You know, it seems like it might not be so more the fundamental research, but more research that's addressing clinical needs, clinical problems. Can you maybe comment on that?
Correct. So if anything, as a Hamlyn Center, we would like it to be even more clinically led and a translational effort in pursuit of solving a clinical problem. So there are many research groups across the institution and many research groups worldwide who also do a lot of fundamental work that is important to us. But especially in the context of the Hamlyn Center, I think translation and clinical pull are the emphasis, and it is enabled by the fact that it's very much plumbed into the clinical environment, which hopefully gives it, one, the clinical pull, and secondly, allows us to embed clinicians at every level of the research and development process. So for example, we heavily rely on a role which is the clinical research fellow role. I think there's something similar in the US, who is the clinician with a research mind that has still got the capacity through training to spend a significant portion of their time working with the engineers. And at the same time, they spend enormous amount of time next to the clinician, whether doing patient care or in the operating theater, so that they can act as the linchpin between the seasoned clinician who has the knowledge but not the time, and the research engineering team who need guidance at every step of the way.
And it sounds like you're referring to almost like a translation interface, right? You know, the importance of integrating these PhD students in a clinical environment so that they can learn the language and translate it.
Right.
Is that okay? And this ties me on to like your sources of funding. It seems that if you're addressing clinical needs, you have access to like non-governmental funding, such as industry sponsored. Do you want to maybe comment on that?
Indeed. So I come from the Department of Mechanical Engineering by background, and I think in mechanical engineering there is an incredibly healthy relationship that is a win-win between industry and academia. And we're talking about work across oil and gas and automotive, machinery, and so on. Healthcare is a little bit more nuanced because it is very IP heavy. And so striking the right balance between a healthy relationship with industry that is large and, let's say, tight, and the need for a larger company to protect the IP that is easier to leak than other forms of knowledge and know-how, makes it harder to strike large substantive relationship with companies. And I have to say, personally, we haven't been successful in large industry partnership, but obviously collaborations, yes. Yeah, plenty of those. I think in a future not so distant, a more meaningful and a larger relationship with industry is important, because it's a very powerful mechanism to get technology from bench to bedside in those instances where spinning out and commercializing in first person is not an option or is not appropriate.
Okay, and you want to maybe comment on the actual process of how you guys go about spinning out like IP and licensing options? You know, is it developed first in-house and you already have a partner in mind who's maybe funded it, or is it you have something then you go and seek a commercial entity to take on the baton?
So anecdotally, I still think the US does it a little bit better than the UK in general. But within the UK, I think Imperial is quite enlightened in the way they're trying to approach technology transfer. And of course, we've got a dedicated enterprise team that works with inventors and entrepreneurially minded researchers and academics to choose the right option. We generally have two main options. You can either offer the institution a smaller proportion, and from the top of my head, I can't remember what number it is, of a spin-out company, but they have absolutely no active role within the company that you're forming. They just allow you to license the technology that has come out of the institution so that you can commercialize it. Or you can offer a larger proportion of the company to the institution that then actively engages in supporting the company through elements of the board and active engagement with decision-making and so on. The last one, of course, licensing, for which there are established rules. So large company X is interested in a particular piece of IP that is usually marketed and advertised by the institution, and then there is a mechanism to either license it exclusively, non-exclusively, and so on. That, for example, is how we struck a deal with Magnet, who is not a company of Imperial College, but rather a company in its own right.
Understood. Now we're heading into our last kind of 4 minutes here, but I'd love to know more about your story with Acrobot, right? I mean, it sounds like it went the full from bench to bedside, and I think, you know, when you're on site here, I think tomorrow, the day after, we can go into that more details, but looking back at that whole story, can you maybe give us like 2 big pain points, like bottlenecks, that were the hardest part of that overall journey?
Yeah, I mean, if I look back at it, even now, I think the main issue that we had early on in the early 2000s, when all of this was sort of taking shape, is that we were not working with a clear and unequivocal clinical need. We were trying to produce the most accurate and the more precise and the most reliable system for surgery. And in doing so, we created a system that was very cumbersome and very expensive, when in reality, it wasn't clear then, and in fact, it is not even clear now, whether that degree of accuracy is needed for the type of arthroplasty, for the type of surgery we were performing. And that is because, of course, human beings are not like a door. If you injure a limb, if you break a bone and you pin it together, it will heal, right? So we are in one of 2 camps. Either it doesn't really matter to get a degree and a millimeter accuracy because the human being has got a capacity to remodel and adapt, whereby the last degree and millimeter doesn't count, or it matters and we're not yet able to capture that nuanced difference because, of course, the backache you experience 20 years down the line, nobody correlates to the fact you may have had a suboptimal implant many years before, right? So all of this is still in the making. I would say that 20 years down the line, we now understand it much better than we did in the Acrobot days, where really we were sort of making it up as we went along. Not pointing fingers, because I absolutely believe it made my career. The experience of the good, the bad, and the ugly so early on in my career, especially the experience of being in an operating theater and deploying this type of technology on people, has completely given me a unique take on how I then progressed career-wise for the subsequent 20 years. And that's why probably every researcher that comes this way, if at all possible, spends some time in the operating theater, because there is no better way to really get a feeling about how complex the environment is and how you can approach trying to be helpful.
Superb. Well, I think that's bringing us to the end of our talk. I'd just like to thank you again, Ferdinando, for joining us. Good luck in London. Please give the motherland a little kiss from me. I hope to be back there soon at some point.
Stuart, I'll see you late tomorrow or the day after tomorrow, and thank you for the invitation. I was very happy to join.
I'm looking forward to it. Thank you, sir. Goodbye.
Thank you.
Okay, so we're right on time. Our next guest is Dr. Tom Ranzani. He is from Boston University, and he is here to talk to us today about enabling advanced percutaneous beating heart procedures through soft robotics. Tom, are you there, sir?
Yes, thank you. Thank you so much for the invitation. Let me share.
Looking forward to this talk.
My slide. Thank you so much. Here it is. Hopefully you can see my slides okay.
Are you in Boston now?
I am.
Okay, superb. All right, let's hear it.
Thank you. Thank you so much for the invitation. It's such a pleasure to be here. I'm Tom Ranzani. I'm an assistant professor in the Department of Mechanical Engineering at Boston University, where I lead the Morphable Biorobotics lab. And the research within my lab mostly focuses on soft robotics. And what are soft robots? So basically, soft robots are designed taking inspiration from natural organisms and how natural organisms exploit the softness and compliance of their body to operate in very complex and unstructured environment. And these are really led to a paradigm shift in robotics, where we started integrating these soft components into our robotic design. And this allowed us to sort of have better manipulation of complex, delicate objects, have impact resistance or body reconfiguration. All things are very, very hard to integrate into rigid systems. And one of the core applications of soft robotics is in medicine. And if you think about it, it makes a lot of sense. So you can now start designing your instruments with integrated compliance and softness, and that makes them particularly well suited to be in close contact with humans. And this, of course, has application in wearable, assistive functionality of organs, or even navigating through natural orifices and cavities, such as the colon or the vasculature. What we're doing in my lab is really trying to explore this potential of soft robotic technologies within the space of medical robotics. And so we're still in the phase of sort of a exploratory technology in this sense. And we're doing this for a variety of different applications, ranging from laparoscopy, where this technology can really allow to increase the dexterity of instrumentation with respect to the conventional laparoscope, but also to have an inherently safe grasping of delicate structures within the abdomen. We're also working a lot within the endovascular space, which is going to be the focus of my talk, and also wearable. But so, as I mentioned, as I entitle my talk, I would like mostly to focus and present the work that we're doing for beating heart procedures. And I don't have to convince you of the motivation and the impact of cardiovascular diseases, but we're particularly focused on procedures that needs to be done on the heart. And indeed, those are and especially looking at bulk disorders and procedures that require some degree of manipulation complexity. And because of these complexities, too often they're still performed through an open surgical approach, which is a very, very invasive approach. Not all patients are well suited to withstand it. It consists of opening up the sternum, accessing directly the heart, having extracirculatory circulation. So it requires, so after that, the patient has long recovery times. Procedures can last a lot of hours, very expensive to be run. And again, not all patients are well suited to withstand that. And so what's the alternative? What's the minimal invasive alternative to that? Is using catheters. And catheters are just small millimeter scale sort of tools that you can insert through the periphery of the vasculature and then navigate inside the heart. However, it's very complicated to have achieved the same level of complexity in terms of like manipulation and force transmission with respect to what you could do with an open heart approach. And mostly because those tools are very limited in dexterity, force transmission, they don't have any sensing on board. So it makes it very, very challenging. We specifically identified 3 core engineering challenges that make operating on a heart in a minimally invasive fashion while it's still beating so challenging. The first one is the size discrepancy. So the instruments needs to be small enough to go through a peripheral access point, but then once they get into the heart, the workspace is much larger. And then because of the initial size constraint, their workspace can be limited as well as their force generation because the small scale limits the kind of actuation that you can integrate on board. The second one, you have a moving workspace. So the heart, if it's beating hard, it's continuously contracting, and you have pulsatile flow. So that, of course, affects stability and positional accuracy. And the final one is remote tool operation. So accessing the heart through a peripheral location means that the mechanical ground is very far from the point where the catheter is actually applying the forces, making force transmission, again, a big challenge. And so how do we sort of tackle these challenges? So we've developed this multifunctional soft robot to sort of address all these different engineering challenges. And our approach relies on two key elements. The first one is a temporary stabilization, again, the superior vena cava. We're mostly targeting right side procedures within the heart. And the second aspect of it is the active tool guidance to sort of restore dexterity. And we demonstrate the potential of our application through two key applications, which have very different sort of clinical requirements, but sort of show the versatility and the potential of this platform in addressing current challenges in percutaneous beating heart procedures. So the first one is coronary sinus pacemaker lead implantation, which require a high degree of accuracy and precise control of positioning. And the second one is tricuspid valve annuloplasty, which combined with accuracy actually also requires some degree of force transmission. And so the concept here is shown through this this overview of the platform. This is work led by my PhD student, Jacob Rogatinsky. And so the platform consists of, hope you can see my mouse, but it consists of a stabilization system that you can see here that again allows you to stabilize the robot at the entrance of the heart. That's sort of providing mechanical leverage at closer with respect to the point of application of the force. And the second component is this soft manipulator, which is used to guide standard interventional tools pass through its working channel. As you can see, the stabilization can be deployed at the entrance of the heart through a simple tightening of a cable, and the control of the robot is given through these 3 syringes that inject saline solution into its inflatable chambers. The system has radiopaque components to be able to be seen under X-ray fluoroscopy. So getting a little bit more into the details of the 2 key components. So as I mentioned, the stabilization part and the soft robot itself. And so the stabilization part is really key to improve stability and force transmission. So the ability to really sort of create this mechanical ground close to the application of the force is really critical to achieve this. And this is done through, this is fabricated through a layer by layer process where we sort of laminate stainless steel for structural rigidity. We have Captain, which is polyimide for sort of flexibility, and then everything is coated through a soft layer. So we sort of laser cut all of this. We selectively bond these different layers, and we wrap it around a 3D printed multi-lumen tube, 3D printed with biocompatible materials. And this multi-lumen tube contains all the sort of fluidic channels for the activation of the soft robot, as well as the central, the working channel of the robot. And you can see here, we obtain this structure that upon pulling the cable sort of deploys into this frame-like structures, and it's reversible. So if you release the tension, it will go back to the undeployed configuration. So it's sort of a controllable deployment stand, if you can think about that. And so we tested, of course, the safety of this. This has been done in collaboration with our clinical collaborators at Boston Children's Hospital. We're, of course, concerned about possible cause of a pressure drop, of increasing the pressure within the superior vena cava. And so we tested how much pressure was induced by the device while in use. And you can kind of see here in the plot that actually the pressure change, whether is deployed or undeployed, is within the measurement error of the pressure sensor. So it's within a few millimeters of mercury. So no pressure drop was caused by the device. We also test possible mechanical damage caused, and we test that. I mean, of course, we sort of estimated the stresses and make sure that they're below the threshold for causing damages, but we actually validated that in vivo. And what you can see here is an explanted superior vena cava after 4 hours of testing with deployment, with multiple deployments of the stabilization mechanism of forces applied to that, and no sign of damage was found on the tissue. And so in terms of functionality, again, what I want to stress is this really allow you to better apply forces distally. And it does that by creating this mechanical ground. We tested this in this figure over here. We have two plots. In both cases, we have the stabilization deployed on a superior vena cava. It's an explanted porcine superior vena cava. And then we sort of try to apply forces axially or radially. And we see that in both cases, we're able to withstand Newton level forces, which is pretty promising. And so we move forward to the second key component of the robot. And the second key component is the soft manipulator. And the soft manipulator is fabricated through a process we developed a few years ago that consists basically of stacking thermoplastic layers which are individually laser cut with thermally insulating material, Teflon in this case. And so you sort of stack them one on top of each other, and you use the thermal insulating material to sort of shield heat transmission from one layer to another. And so you create these laminates, which you can kind of see here coming together into this video, where you stack all these different layers together. And then once you have this laminate, you put it into a heat press, which provides controlled pressure and heat. And this allows basically to melt the areas that are not shielded by the Teflon between the layers, and create basically these inflatable balloons that have a pre-programmed shape. And the shape is given by the way we laser cut each of the individual layers that compose them. So you can kind of see here, so you can create like a singly extending balloon. They look like, we call them stacked balloon actuators because they really look like a series of balloons, one stacked on top of each other. And you can create multi-degree of freedom structures, as you can see here on the right. And so the key benefits of this structure is that they're really just inflating through a geometrical change, which makes them approachable to be modeled geometrically, as you can see here. So we have geometric models of them. We have finite element model to sort of control their shape. Also, because their deformation is mostly geometric, they provide very minimal energy loss in their function, while they're still providing Newton level force generation. So up to 5 newtons of force for an actuator that it's a little over 1 centimeter in size. And the other interesting thing is that their initial volume is just due to the thickness of the layers, and layers are few tens of microns each. And so it makes this structure that can be initially almost no volume and take no space, and then they just inflate, as you can see in this kind of cute little demonstration of 3 of them stacked together. And so we have this actuator now, and we can combine it with this stabilization mechanism to develop this platform. And you can kind of see here, this is stabilized over a clear tube, just for visualization. We have the multi-lumen tube here, and the soft manipulator that is being oriented to point towards these small holes, and then has a working channel in the center, as I mentioned, through which you can pass through standard catheters. You can also see that we have those metal components that are just for visualization under fluoroscopy. The second video, and it's coming up in second, actually shows the importance of the stabilization mechanism in force transmission. And so you can kind of see here, so now the robot is stabilized through this clear tube, and it's pushing through this syringe to fill up this other syringe. And when it's stabilized, force transmission is very effective. So you can see it's filling up. When it's not stabilized, the robot actually pushes backwards. So it's not able to effectively apply forces on the target. And so getting a little bit more quantitative here, so you can kind of see the range of motion of the soft robot at the end with an instrument inside its working channel. We also compared its actual workspace with respect to a model of the right atrium provided by our clinical collaborators. And we can see we can actually map every point within the right atrium. Additionally, we sort of validated our force transmission ability. So in all these plots on the right, you can see the stabilization is deployed on an explanted porcine superior vena cava here, and a different robot configuration, we sort of push over a force sensor and measure the force that is able to generate. And in all cases, we're able to generate Newton range forces. One of the other important aspects, so I mentioned in the challenges, it's to be able to deploy this instrumentation through a peripheral access port, which poses a strong constraint over the size of the robot. And of course, our platform has the stabilization mechanism that can be easily deployed, but the soft manipulator, to be able to generate the forces required, needs to be on the centimeter scale. So we're mostly targeting to go fit through a 24 sheath because that's what's the standard used for example, tricuspid valve repair. And so we develop a strategy to be able to fit the whole platform through a 24 French sheath. And the strategy consists of, sorry, the video is freezing right now. But the strategy basically entails fixing the length of the soft manipulator and then applying vacuum to it. And by applying vacuum, what it happens is that the system basically shrinks radially, and by shrinking radially, it can still fit the 24 French constraint. My apologies, I have to exit 1 second and start it again because the video froze. And we're having some technical problems here. My apologies.
Wouldn't be a conference without at least one tech problem.
Yeah, I'm not sure what it is happening. Would you mind if I rejoin in 1 minute?
Yeah, I mean, we're almost out of time actually there, Tom. We've got like 5-6 minutes left. So I mean, do you want to go straight to Q&A? Because I'd hate to lose you again. You know, if you're gone, then you're gone forever. Well, in this conference, should I say?
Okay, sure. Yes, absolutely.
Okay. Right, so you gave us a really good overview there of your soft robotics program, and kind of tying in with our first guest, Ferdinando Rodriguez. I'm curious, you know, can you define the clinical needs that you guys are addressing? But I also appreciate that there's probably a lot of fundamental research that you guys are involved in as well. So maybe comment on that if you can.
Yes, that's the part I didn't have time to get to.
Okay.
Actually, yes. So the clinical needs. So it starts on a sort of a two sides here. So on one side, we by talking a lot with clinicians, we sort of started recognizing what are the core challenges in sort of beating heart procedures, right? So in terms of stability, force transmissions, of the one that I've introduced before, and so we're interested in sort of developing a platform that could provide a new approach to trying to tackle them, right? So right now, people have been looking at way to just add functionality to catheters, but catheters are somehow inherently limited because they're still very thin structures, and because they're very thin structures, they limit the kind of actuation you can integrate. They limit the things that you can basically embed on board, so that's on one side, and then as we were developing this platform, we got a lot of excitement by clinicians on how this could actually tackle specific clinical problems, and we've been looking at coronary sinus lead implantation or tricuspid valve annuloplasty, and that led to a sort of refinement of the technologies as we go. So as we started demonstrating how this technology could help, then we started sort of steering towards specific clinical problems and optimizing it towards specific clinical problems. And that's actually what we're doing right now.
And who's your clinical lead on this, if you have one, if you don't mind me asking?
Oh, we have multiple. Yeah. We have two clinical leads at Boston Children's Hospital. So Dr. Debbie Hogginson and Dr. Dagmar. Yeah. Oh,
super. Now, I know we actually discussed this as well about the preclinical cadaver beating heart model. Obviously, you know, for your preclinical studies, I believe you'd be using an animal model, sorry. But what do you want to comment on what models you actually use, whether it is animal or if there's something out there for cadavers, etc.?
So we're actually using pig models. So we're using large Yorkshire pigs for validating this, and we've done actually successfully our first in vivo test like a few weeks ago, where we actually demonstrated coronary sinus cannulation. Yeah, and we have, of course, a bunch of other sort of in vitro testing that we're doing. But of course, the final in vivo validation is the most important aspect. We have laid out another 5 live animal testing coming up in the next few months.
And just for our audience, just so they're aware of problems, etc., do you know of any cadaver beaten heart models currently out there?
I'm not aware of that, although I have to say I haven't fully looked into it too much, just because we're still sort of at the early phases of validation. We've finalized developing the technology, so we're really like at the early phases of understanding this.
Got it. And I've got a question regarding your choice of materials. Now, obviously, looking at the FDA regulatory affair approval pathway, I'm assuming that would be easier for you guys if you have materials that to some extent were already FDA approved. So how do you work around that trade-off? Like, what materials are you utilizing and are they FDA approved already?
Oh, that's an interesting question. So we haven't started looking into FDA approval. We make sure that every material we use is biocompatible. And that's been our focus so far. We would be interested in looking into FDA approval in the future. We filed a provisional patent application on this device, and that's definitely sort of a road we're pursuing, but we're not yet at the sort of FDA approval route.
Got it.
In terms of materials yet.
And I guess my last question is your actuator mechanism. I mean, obviously, there's a lot of different kind of physical parameters and options for that. You could use, like air, water, thermal activators, photonic activators, and whatnot. So you want to maybe comment on the route that you chose and why?
Yeah, so we chose fluidics because it's a very sort of safe way of actuation. The robot requires very low pressures, and you can inject saline solution, which even if you have a leak, you still have a leak of saline solution within the heart. We also chose, so there's no currents, there is no heat generated, so there is no changes in sort of physiological parameters by using the robot within the beating heart. Fluidics is also very good at transmitting forces. So one important thing that we're looking at is how can we sort of restore Newton level force transmission within the beating heart, and fluidics it's very good at transmitting high forces, especially with this strategy where you can probably still see on the screen how the robot can be shrinked to a very small space for navigation, and then once it's inside, you regain sort of a large surface area, which allows to transmit forces very effectively on a target. So I guess the two key features here are the safety of the fluidic actuation, its ability to transmit large forces, and the ability to fold it into a very small configuration and then deploy it inside the heart to restore force transmission once inside.
Wonderful. I appreciate that detailed response there, Tom. Well, at the end of our time, I just want to thank you again for coming on the show, and good luck. You know, I'm sure we'll have you on here again if you're interested, and thank you very much.
Thank you so much for the invitation.
Okay, and now on to my next guest. He's going to be talking about human skill augmentation and robotic assisted surgery. We have Dr. Alaa Eldin Abdelaal, who's currently working at Stanford University. Alaa, pleasure to have you on the show, sir.
Thank you very much for the invitation. It's a really exciting symposium. I'm very happy to be part of it.
It's good to see you again. So, love to learn about augmentation and robotic assisted surgery. What are you guys cooking up in Stanford?
All right, so let me share my screen. Okay.
Okay.
Right, can you see my screen?
Yep, looks good.
All right. So what I'd like to share with you guys today is essentially the work we have been doing over the past few years on building systems and algorithms to augment humans as they perform robot-assisted surgery tasks. That's really motivated by some of the stark statistics I was very surprised to learn about when I started working into this area. So despite the fact that worldwide, surgeons perform around 230 million procedures every year, the world is yet short of an additional 140 million procedures, just due to the shortage in surgeons. And even in places like the United States, where you would get, better access to surgical expertise, it has been estimated that essentially medical errors are the third cause of death, killing around 250,000 Americans every year. This makes medical errors, the third cause right after cancer and heart disease, and well before essentially stroke and car accidents. 40% of these errors, unfortunately, happen inside the operating room, and 50% of them, of the complications resulting from these errors, are really avoidable. So that's why I have dedicated, the mission of my entire research career to essentially trying to fix this problem to improve surgical practice. And basically, my main contribution lies into two instances of the skill augmentation spectrum, if you will. The first one is during the skill acquisition phase, i.e. during surgical training or surgical skill assessment, where I've been designing interfaces to improve the motor skill learning aspect in surgery. And the second instance is during post-execution, where I have been designing autonomous systems and algorithms to perform some of repetitive tasks for the surgeons. So think of suturing or automating the motion of the camera so that surgeons can focus on the more demanding ones. And just for the sake of time and for the context of this symposium, I'm going to focus today on my work on skill acquisition. And as you all may very well know, there is a vast body of literature in this area. So there is this direction of having an expert in the loop kind of training. So an example of this is something like this dual console robotic platforms. A main surgeon would sit on one console, and the trainee would sit on the other one, and really the training would happen on the spot. And then there is, paradigms where they do not require, having the main surgeon and the trainee at the same time, same place. Something like, video-based coaching, where you would imagine in a virtual reality simulator like the one I'm showing here from Johns Hopkins University, the trainee would be, teaching or performing a simulated suturing task, for example, and they would have the ability to press into an icon, and this essentially would lead to showing a pre-recorded video of an expert performing the same task. And the goal is that by doing so, you would make the training more efficient. And in terms of data related stuff, so there is this operating room black box system that came out from the University of Toronto, using the black box metaphor from the aerospace industry, where the idea here is that you would place multiple cameras, as you can see here, outside the patient abdomen, inside the intercorporeal camera, and essentially they will record all what's happening inside the patient abdomen and outside in the operating room, and essentially gather all this data, analyze it for things like error analysis, training, and skill assessment. But really our key observation, looking into this vast body of literature is that at some level, robot-assisted surgery basically replicates what happens in an open surgery setting just through smaller incision, ignoring many of the robot's unique capabilities. And just let me give you one example of what I mean by that. So if you take the design of the robot, for example, and this is essentially the patient side card of the DaVinci surgical system, the most widely used system in this area, you would notice that, because they wanted to replicate in part, the open surgery setting. So in an open surgery setting, you'd have a main surgeon. The main surgeon would have only one pair of eyes, and the equivalent of this one pair of eye is essentially one arm holding the camera. But if you think deeper about it, you would notice that robots actually can do better. Robots can have, for example, more than one cameras. And this essentially leads to, the key insight that guides my entire research agenda, which is, the very fact that robots and humans are two different entities, meaning that robots can have or already have unique capabilities that are sometimes completely different from humans. And really what I do during my research is that we identify some of those capabilities and we leverage those essentially to design, state-of-the-art system to augment humans in robot-assisted surgery. And for the context of this talk, I'm going to essentially walk you through a couple of the unique capabilities we identified and leverage in this domain. So the first one is the very idea that robots, unlike humans, can have more than one pair of eyes. Essentially, they can have more than one camera, unlike a human surgeon in open surgery setting. They can also have an adjustable interpupillary distance. You can play with the distance of two cameras viewing the scene in 3D, unlike the interpupillary distance of a surgeon, of a human in general, that essentially it's fixed. You can't really play with that. And in the rest of my talk, essentially, I'm going to give more details about these two capabilities, what I really mean by them, and how we leverage those essentially to essentially improve the human skill augmentation aspect in robot-assisted surgery. So let's start with the first one. So the current camera systems in robot-assisted surgery, most of them are essentially 4 degrees of freedom robotic manipulators. They have been serving us so well so far, but there are cases where they are not, dexterous enough, essentially, in order to view hard-to-view areas in the scene. And this really started from, interacting with our surgeons. So they told us, for example, in cases like partial nephrectomy, the current degrees of freedom of these robotic cameras are essentially limiting some of the things that they would like to do. And hence there was a clinical need for having essentially, a camera that provides more degrees of freedom. So combining this clinical need with essentially our insight that, a robot can have more than one pair of eyes, what we really did is that we designed an additional camera that would be used essentially in addition to the original endoscope of the surgical robotic platform that provides more degrees of freedom and provide an additional view of the scene. And we call our camera design a pickup camera design. And you can think of the design as essentially, you are having a cylinder. The cylinder essentially would be inserted vertically through the same incision that is being used to insert the surgical instruments. And once it's inside the patient abdomen, it will be picked up by one of the normal surgical instruments you would use in your robotic platform. So really inserting it, vertically means that there is no disruption. There's almost no disruption in the workflow. And then on the body of the camera design, we do have the vision sensors. We do have here, as you can see, 2 vision sensors to provide a 3D stereoscopic view of the scene. And really a key aspect of our design here is what we call a spatial mating surface, which is essentially this part of the design that allows essentially for repeatable grasping by the surgical instrument. So in more technical terms, the spatial mating surface essentially allows having a known and rigid transformation between the coordinate system of the tool holding the camera and the coordinate system of the camera itself. And compared with existing cameras, our backup camera design allows, you can see here, to have 6 degrees of freedom of control, which essentially means that now surgeons can view these hard to view areas that they weren't able to view using 4-degree freedom robotic endoscopes. So building on top of this, we wanted to see, okay, would having, this idea of multiple cameras providing multiple views, would this be helpful in something like, surgical training? And to do this, essentially what we were really inspired by what happens in soccer. So if you're a soccer fan like myself, you would know that, a few years ago, they introduced something called VAR, or Virtual Assisted Referee, where the idea here is that if, a referee is not sure whether an incident is a foul or not, what they would do essentially is that they would review or rewatch the incident on a screen from different perspectives, coming from different cameras, and the goal is that by doing so, they would make a fairer decision. So in a sense, what we designed is the surgical version of this virtual assisted referee. And if you're wondering how this could look like, it can look like something like this. So this is on the Da Vinci surgical system, for example. And what you see here is a picture-in-picture view of a task. Essentially, the bigger view is coming from the original endoscope of the surgical robotics platform. And the smaller view is coming from our own backup camera. And we wanted essentially to test this in a training task. So we chose this task that you see here. It's called a wire chaser task. It's essentially a task where you would hold this ring, and you'll move from one side of the rail to the other side of the rail without avoiding touching the ring with the rail. And it's used essentially to train on the maneuverability skills of controlling the robotic manipulators for trainees. And you can tell really just from this instance that I'm showing to you that if you only see the bigger view alone, it's really hard to tell from this view whether the ring is touching the rail or not. But now that you do have essentially the second view, you can tell that no, I'm not touching, and then I can continue, through the rest of this task. So to evaluate this, what we did is that we conducted a user study where we had 2 groups of trainees, a single view group and a dual view group. So they both trained on performing this task. During the training phase, the single view group was only shown, the task from the perspective of the original endoscope. So only the bigger views that they see. And the dual view group were able to see the task from the 2 views in a picture-in-picture, as you see here. And then essentially we invited them to come and do a retention test after their training. And during this training, the 2 groups essentially can only see the view coming from the original endoscope of the surgical robotic platform, meaning essentially the bigger view alone. And the main results that we found is that the dual view group essentially was 35% more accurate, essentially committing less errors. And errors here refer to the instances of the ring touching the rail. And essentially, they were 25% faster than the single view group. So we think that there is, a huge potential for this line of work. So, for example, one potential impact here is actually in the arena of virtual reality simulators for surgical training. So if you think about it, the designer of the environments in these simulators essentially know their environment really well, and could be relatively very easy to add an additional view as a picture-in-picture, for example, to the trainees. And our results suggest that by doing so, essentially, we can have a better and more efficient training process. And in real cases, we think that having this additional intercorporeal cameras that we proposed and adding it, integrating it in systems like the OR black box system will also provide more views of what's happening inside the patient abdomen, something that can be very, very useful for surgical skill assessment and error analysis. So really, this was, as a very first simple yet unique capability of robots, the very fact that robots can have one pair of eyes, and how we leverage this essentially to improve something like surgical training. So now let's switch to essentially the second case, where essentially this idea of having that robots uniquely, unlike humans, can essentially have adjustable interpopular distance. So you may think, okay, so why this idea of interpopular distance would be important in the first place? It's really important because we know already from the teleoperation literature in general that increasing the distance between two cameras viewing a scene in 3D, they call this distance the camera baseline distance, essentially is associated with improving the performance. So for example, in the 90s, it was shown that if you increase the distance on the x-axis here between two cameras viewing a virtual task, the error on this task would decrease, as you can see here. A similar trend also was noticed when using a head-mounted display. So really, knowing that in the general teleoperation literature, we wanted to see, okay, how can we make use of these findings in a robot-assisted surgery setting? So a naive approach would be, okay, let's do this with the existing robotic manipulators, right, in a surgical robotic platform. So what you see here is another view of the endoscope of a surgical robotic platform. So really, if we would like to increase the distance between these two cameras viewing the scenes that provide for the surgeon's 3D view, this would mean that we would have to have a wider distal end of the robotic manipulator, which essentially would mean that we would need a wider incision through which the surgeon would insert this endoscope, which partially at least defeats the idea of minimally invasive surgery in the first place. So in other words, we can't really directly translate this parallel result to a surgical environment. But now using our backup camera design, we don't have this limitation. And the reason here is that, remember, the camera is a cylinder. You will still insert it in a vertical way. So there is no need to, widen the incisions by any means. But then the cameras here, the vision sensors themselves, are essentially placed on the side of the cylinder, which means that we have ample space here and ample space there to play and increase the baseline distance between the camera. So we can essentially test this idea of playing with the baseline distance of the stereoscopic cameras while maintaining the minimal invasiveness aspect of the surgical procedure. So to push this further, what we did essentially is that we conducted a user study with the goal of studying the effect of having larger camera baselines on the very task of perceiving depth in surgery, something that's very, very important. And what we did here is that we had 4 identical camera designs, except, so as you can see here, they are identical except for the baseline distance between the 2 vision sensors. So we have 10 millimeter, 15 millimeter, and 20 millimeter, and 30 millimeter distance between the vision sensors. And what we did in this study is that we had a depth ranking task where essentially we recruited subjects and they can essentially view, this is what they see essentially, a board of bins of different lengths. And we wanted them to give us an order of, the length of these pins from the shortest to the tallest. And for each subject, essentially, they would see this board essentially under the 4 camera or the 4 baseline conditions that I have just described. And really, to get this right, the resolution of depth perception that a subject would need is 2.5 millimeters. So essentially, after each subject, would view the board under each of the baseline conditions, they would give us a score, give us an order. We compare this order essentially of the length of the pins with the ground truth order that we already know, and we use Hamming distance to measure the similarity between these 2 sequences. So Hamming distance gives a score of how similar two sequences are, with the idea of a lower score would mean better performance in our case. And really the main finding of this work was that essentially, as we would expect, increasing the baseline distance between the 2 cameras essentially led to, as you can see here, improvement in the performance, because we have now lower scores, and lower scores mean better performance, with essentially having a baseline distance of 20 millimeter being the sweet spot. So again, why this would be important? We think this would be important because it essentially provides a shift really in the endoscopic design philosophy. So as I mentioned, essentially current endoscopes are following what we can call end-firing cameras, meaning that the vision sensors themselves are placed at the distal end of the robotic manipulator. But essentially, what our work has provided evidence to is that it can also be useful to follow what's called the side firing camera design philosophy, where the cameras are placed on the side of the design of the camera system itself, not at the distal end. And another really cool aspect here is that instead of making separate cameras, each with their own baseline distance, there's nothing that hinders us now essentially from having what I like to call an adaptive stereo camera baseline, where the idea here is that you can dynamically change on the spot the distance between the two vision sensors here based on the working conditions or the preferences or the needs, the preferences of surgeon or the needs of the surgery. So really the main takeaways that I would like to leave with you today is that we are providing proposing a different way of thinking about how we use robots in robot-assisted surgery. And it's really revolving around this idea that robots, unlike humans, can have very different unique capabilities. And leveraging these unique capabilities can allow us essentially to better augment humans in surgery. And I give you a couple of examples. So I showed you that the very fact that robots can have more than one pair of eyes led to our backup additional camera design that I showed you can lead to better surgical training. And that the very idea that robots, unlike humans, can have adjustable interpupillary distance can lead essentially to better depth perception with a resolution, according to our user study, of 2.5 millimeters. And with that, I'd like to thank all my collaborators and the generous funding I received for this work and my ongoing work. And with that, I'd like to thank you very much again for the invitation. I'll be happy to answer your questions.
Well, thank you very much for that. That was a really good talk there, and I know we're kind of a little bit tight for time. So, one question, I guess, going right to the beginning. I'm just curious how you guys initiated this project. Was this from direct clinical needs? Clinicians come to you guys saying, "Hey, we need better ways to assess our skill training or skill acquisition." You want to maybe comment on that?
Yes, so it really started exactly like what you have just mentioned. So essentially, we're specifically told that, in something like partial nephrectomy, when, there's a tumor and this tumor is at the backside of the kidney, it's really hard to use a 4-degree of freedom manipulator to essentially view the back of the kidney. Because if this is the kidney, you'd like to go in this side. And, doing this with a 4-degree freedom manipulator is very hard. So it would be very useful, to have a camera that would provide, more degree freedom to see it. And I think one analogy, we were discussing is something similar to what would happen, when you go to a dentist. Remember when they would use, this very small mirror that can show them, the back of one of your tooth or something like that. So they wanted something like this, and this is, I think, how the project took over.
And could you maybe comment as well on how you can see this type of technology really integrating into VR-based simulations, and maybe talk about the technical aspect? How is it done? Do you do it in Unreal or Unity, then blend it in, or maybe just comment on that?
Well, so the beauty about applying this work in a virtual reality setting, that you don't really need the additional camera or the backup camera design as a physical hardware. You just essentially need to know your environment. So a virtual reality environment would be created, right? Whether it is Unity or something else, and then because you know your environment, right? You can, at least I assume, it would be a low-key thing essentially to, have a different version of this environment, right? And show it as if you are showing the scene from a different view.
I do apologize there. Just I'm talking in the studio and I shouldn't be. So last question here, I guess, is, you know, where do you see all this technology going? And the reason I'm saying that is I have seen a lot of research and innovation around this area of surgical skills acquisition, right? And it's these things are popping up, so they're gaining momentum, they're gaining speed. When do you think we're going to start seeing it actually in the clinic and people using it? And where do you think it's going over the next few years?
Well, I would say we are already seeing it. So, you know, I'm aware that, you know, surgical robotics companies now are, you know, leveraging the very fact that they are collecting so much data really through these, you know, robotic systems, because what they do is that they have digitized surgery, right? You can know everything that's happening in surgery. Okay. And I think one promising aspect that's being, you know, used right now is this kind of personalized kind of trainers or skill assessor. Right, so something that will measure based on your data, you know, day-to-day data, you know, how good you are in performing a task, and then gives you, you know, some specific recommendations of, you know, maybe your economy of motion needs to be improved, or maybe you touched an area that you shouldn't touch or something like that. So I think this is happening. This is happening now. Moving forward, I think one interesting venue would be, you know, the integration of findings from neuroscience research and motor skill learning research on how people acquire, you know, motor skill, and then leverage this essentially for the new generation of surgeons and trainees can be very, very useful and promising.
Okay. Well, Alaa, it's lovely to see you again. I'm really looking forward to meeting you at some point, you know, face to face. Next time you're in Houston, come and give us a shout, or maybe I'll see you guys up in Stanford. So thank you again for coming on the show, and I'll see you soon.
Thank you very much for inviting me. Bye-bye.
Okay, so we're going to switch gear a little bit now and go into our clinical side of robotics. And rather than speak with Dr. Ramirez at the moment, we're going to speak with Dr. Saifi. As you may know, it's tricky sometimes coordinating schedules with surgeons, so we do appreciate their time spent in the studio. So it's my absolute pleasure to introduce Dr. Comron Saifi from Houston Methodist Hospital.
Thank you for having me. I appreciate the honor to speak with everyone today about this important topic. I'll be discussing advances in navigation and robotics in spine surgery. These are my disclosures. So I am a consultant for Medtronic who does have some robotics and navigation devices that we'll be discussing. So as an overview, intraoperative imaging, spinal navigation, including augmented reality and spinal robotics are the three areas I'll touch upon today. And you know, the overall purpose of all of these technologies are really going back to our core fundamental values of safety, decreasing variability, improving our planning and therefore our efficacy in terms of treatment, and then also improving our efficiency and cost. And so anything that can help us achieve these fundamental goals for our patient is really what we want to do. So where has it all started? So everything really started in terms of navigation with fluoroscopy initially. And so fluoroscopy has been the foundation for where we have started with doing surgeries, and in terms of minimally invasive surgery, and just in terms of having safety and reproducibility. And this is a case of mine from several years ago, and we all trained, when I trained in fellowship, we trained using basically K-wires and fluoroscopy in order to do minimally invasive surgery. And this allowed us to do smaller surgeries without doing large dissections. Patients could go home sooner, take less narcotics, get back to work and life sooner. So starting from this journey, we've moved forward now and we've gone towards navigation intraoperative. This is just in terms of fluoroscopy where we started. So allowed us to do really minimally invasive. Radiation, though, is a real concern with fluoroscopy. We have wearing lead vests, which can make it difficult. And then we have the risk of cataract and cancer, both to the patient, staff, and surgeon. And then accuracy is not so reliable with this fluoroscopic systems. So it depends on the patient. If a patient's osteoporotic, we won't see the bone as clearly, or if they have a large body habitus. The other issues are that it is very much tech dependent, and in terms of minimally invasive surgery, there's a steep learning curve for the surgeon. So why do we want to do minimally invasive surgery? Well, I mentioned before that there are some benefits for minimally invasive surgery, and those include lower length of stay, improved return to work values, as well as smaller incisions. But you can see here, this is an image of a patient who had minimally invasive surgery on the right, and the one in the center was open surgery, same exact surgery. And you see all the white in the bottom, and that's really the muscle that is turned to fat in the patient with open surgery, whereas the muscle has remained innervated and functional in the patient with minimally invasive surgery. So moving on now to intraoperative 3D spinal imaging. There are many different options on the market, as you can see in the current slide. And so these are probably 4 of the most common ones. They are quite expensive, approximately $500,000 or so for each system, and they have sort of their own pluses and minuses. So this is an image of what it looks like for 3D intraoperative imaging. And so what we do is we can bring the 3D imaging into the OR in some ways like a mobile CT scanner, and then image the patient intraoperatively. We can also place our screws and then image the patient. So when this technology came out, I would do all of my spinal deformity surgeries, and then at the end I would check all the screws with the CT scanner, and this is just depicting that. So the screws or the markers go in, you can scan and just confirm. And so this is in some ways, as I mentioned before, safety, reproducibility. Every time you leave the OR, you know everything is well placed. But this is checking after the fact. And so moving on to sort of how do we prevent a screw being in the wrong place? How do we proactively make sure that we're doing everything right to begin with and not just checking? So that's where spinal navigation comes in. And spinal navigation has been around now for a while, and it's developed into a fairly mature technology. And these are 3 different types of spinal navigation, different brands. They all have similar principles. This is just a photo of me using it in the operating room. So you can see on the photo on the right, you can see on the screen on the computer in the operating room where the screw is going in 3D, and the image is quite good in terms of resolution. And this is just showing, again, how it looks to the surgeon in the operating room. So we're placing the navigated instruments. So we have a registration device on the patient, and then we have markers on the instruments. And so this can track your instruments as it moves with respect to the patient's body and show you where it is. This allows me to do minimally invasive surgery without fluoroscopy. So this is an interesting example. So typically we use it for screw placement, and this is a patient who had it performed both for screw placement but also for osteophyte resection. So you can see this is the left L5S1 at the bottom. The patient has a large osteophyte there pressing against the nerve root, and then on the right side the same. And these osteophytes are causing the patient leg pain. And these are in a tricky area to resect because what can happen is that the nerve root is directly above it, and so it's an area we want to be very careful with. And so in order to remove this, you can use 3D navigation. So you can see here, this is a photo of the probe, and so I'm 100% sure that I'm on that tiny little bone spur in the right place, and I'm able to resect it. And these are the pre-op and post-op images for that patient, and we navigated not only the screws but also are able to navigate the inner body device that goes in there. So for this surgery, for instance, there is no fluoroscopy taken at all, beginning to end. I don't wear any lead, which is a real change in workflow. And everything from beginning to end is done with navigation. This allows me to do this minimally invasive, and there's just 2 small poke holes that are approximately 1 inch in width on the patient's back, allowing them to go home the same day or the next day. So this is an image of me doing utilizing spinal navigation for spinal deformity, and so you can see that there are multiple. These are called tulips coming out, and these are connected to the screws. But again, I'm just making little stab incisions, and so the surgery is much less traumatizing to the soft tissue. Patients recover much sooner, even for a larger surgery with a spinal deformity. And you can see the tracker on the patient, so that's at the bottom with the 4 arms. And so the machine uses that tracker to know where it is in space. And you can see the image in the background, which shows me exactly where my instruments are going. I can even do decompressions through those little tiny portals, and that's what that kind of snake arm is going around the top. So navigation is great, but it's not without its issues, and workflow optimization is the most important, I would say, aspect of navigation now that the technical issues have been, I think, addressed, in my opinion. And so having a good workflow is critical to any surgical setup, and navigation is no exception. And so it's very important to do so. And so several groups have gotten together using lean principles and Six Sigma to develop systems and really algorithms for using navigation in an efficient manner. So moving on to other more unique spinal navigation. So augmented reality has become a very interesting and important part of spinal navigation. There is also a system called 7D, which uses topographical information to register and allows segmental registration. So one of the downsides of traditional navigation is that it registers the spine as a whole, as one piece, but with the imaging navigation, 7D, it allows segmental registration. So if the bones move during the surgery, it won't affect your accuracy. So looking at augmented reality spine surgery, you can see the top left corner shows the headset. So the camera is where it's pointed A, and then B is the retinal heads-up display. And so you can see what it looks like to the surgeon in the bottom left. So you get an overlay of the spinal anatomy through the lens directly into your vision. This has several advantages. One, the surgeon does not have to look around. They don't get distracted by looking at the screen and then looking back on the patient. They can keep their focus on the patient and see whatever they need to see in 3 dimensions. Additionally, you can see in the top right, this is an image of a patient with a tumor being resected, and they are performing an en-bloc resection, and they can use the augmented reality navigation to resect and perform their osteotomy to have clean tumor margins. And so this is a really interesting application to augmented reality and navigation in general. This is a study looking at augmented reality versus fluoroscopy-assisted freehand surgery, which is, I would say, the most commonly done today, and demonstrating that for accuracy placement, when they graded the screws, I apologize. When they graded the screws in terms of their accuracy, they found significantly higher accuracy with the augmented reality set versus freehand with fluoroscopy, which is the standard. So this is a study that came out of a group at Johns Hopkins where they did an en-bloc resection for a tumor using augmented reality. And they resected, you can see the entire vertebral body, D, on the top right, using augmented reality to perform their osteotomies as I showed in the prior slide. So this can have applications not only to spinal fixation, but also to tumor surgery for spine. So moving on to spinal robotics, which is the next evolution from spinal navigation. There are several robotics. These are 3 examples of those robots, and you can see they are quite expensive. They average around $1 million or more each. And this is a video of how one of those robots works in the operating room. So the robot has an arm. This one in particular attaches to the OR bed and attaches to the patient. The robot then comes out of the casing and it does a scan. The surgeons have the option to do intraoperative planning or preoperative planning. I think the preoperative planning is one of the strengths of this system. Allows you to utilize the CT scan preoperatively to plan your screws, which is what you're seeing here in the animation right now. So you can pick, where do you want your screws placed? What trajectory do you want? How long do you want them? How wide do you want them? And this allows really for ideal screw placement and ideal screw size. So there are studies showing that with robotics and navigation, you can get larger size screws safely. And this can allow for better potential clinical outcomes. So you can adjust all of this, and this is all done preoperatively. And so you can pick however you want to do your surgery. And then when you go into the OR and you register the machine, it already knows exactly what angles to put everything at based on how it's connecting to the patient's body there. And so immediately this arm will go into the exact position that you had told it previously you wanted the screw. The other nice thing is that it basically merges the pre-op CT with an intraoperative fluoroscopy, so you don't have to do intraoperative CT or a 3D spin with this. The downside, of course, is that it does take longer. There's a study I'll show that shows that there's roughly 30 minutes increased time, operative time for using the robot. There had been some issues before, particularly with something called skiving, which I think has been addressed at this point, where the drill could slide based on if there were some shear forces on it, depending on if you angle against a bony surface that's perpendicular, you have no issue. But if the bony surface is highly sloped, you could shear. And that's been solved pretty much by using navigated burrs. So I just want to give an example of a patient that I did with one of my colleagues. We did a robotic navigation, and she's about 18 months out. So this is a 7-year-old woman. She's got a severe spinal deformity. You can see how her spine goes forward, and her posture is very much forward, and that causes back pain because the spine is going forward, the muscles are trying to keep it up, and the patients will fatigue after walking just a short amount. And so what we did was the patient had a 2-stage surgery where she had interbody spacers placed in the front, and then we did the robotic surgery. We did 2 S2AI pelvic screws into the pelvis, and then ran it up to T10. And so this patient is 18 months now, doing great. And the strengths of this are that you can plan beforehand. You can really maximize your screw sizes and lengths, and it allows for better overall biomechanics. So this is what the OR setup looks like. So we have our navigation as well as our robotics. So you can see the camera from the navigation on the left, the workstation for the robot in the center with the reference frame and robot arm. And so the recent combination of robotics with navigation, I think, is where we're heading in the future. And so the algorithm or guide for this is basically you drill or burr initially through the navigated arm, and there have been issues with the skiving, so people recommend using a drill guide with sharp edges. And then the screw placement is done with power through the robot and confirmed at the same time using navigation. So this is a study we published myself with folks at Columbia, Ron Lehman, Larry Lanke, looking at human versus robot. for S2AI screw placement. So we found that there was no difference in the number of breaches, the breach distance, or complications. I would say that the robot had a challenging task because our controls were Dr. Lenke, who is a world-renowned surgeon. But it does show that the robot is able to accomplish this safely and without issue. So the largest meta-analysis to date has used 64 studies with over 11,000 patients and over 20,000 screws to compare robot-assisted and augmented reality to control. And they found that for this meta-analysis, there was less risk of inaccurate screw placement with a clearly significant power, fewer perioperative complications, decreased length of stay, and as I mentioned, increased operative time. They found about 24 minutes increased operative time. For augmented reality, they found a decreased radiation exposure compared to fluoro and robotics. One of the other benefits of augmented reality is it has a much smaller footprint, so there's no large robot. So in conclusion, spinal navigation is at this point a mature technology, and augmented reality is part of spinal navigation that is developing, and I think we'll see more of that in the future. Robot-assisted spine surgery is a developing technology, but it's incredibly promising, and I think we'll definitely see more of that as it matures. And again, the core principles here are to improve safety and reproducibility, which is the goal of these technologies. Thank you.
Thank you, Dr. Saifi. That was phenomenal, actually. I'd love to get a little bit more deeper into the percentage of cases that are currently using image-guided technology in robotic surgery. So it seems like the whole roadmap's there. You know, you have the image-guided navigation, which you were originally looking at 2D browser screens, but it's now been upgraded with augmented reality. Mm-hmm. And then you've got your robotic-assisted surgery that's been developed. So going all the way back, you know, what percentage of surgeries use image-guided navigation? And where are we with the robotic-assisted surgery, and what companies are looking at that?
So it's a great question. There's been an evolution over time that I've seen. So we have, you know, when I was in my training, we typically would do all of our surgeries with fluoroscopy. I never used in my fellowship any image guidance. But as we've continue to evolve, I would say now, at least at Houston Methodist, the vast majority of our surgeries are done with image guidance and navigation. I do spins for all my surgeries at the end to check to make sure all my screws are well placed. And I use navigation for all of my instrumented cases typically. I think robotics is sort of building up, but I think we'll be there soon.
Got it. Now, you made a really interesting point earlier. You said for one of the open surgery procedures, all that muscle turned to fat. So why is that? What's the mechanism of action?
That's a great question. So the speculation is that we denervate the muscle when we do a midline approach. As we take the multifidus muscle and the spinalis muscles off the spinous process, we denervate them, and that causes the muscles to go into fatty atrophy.
Got it. Now, as part of Mirren, you know, we always try our best to pull in platform technologies that we can offer our surgeons, clinicians. And one of the companies we work with is Insight Surgery, and they're able to convert DICOM images and to basically segment, render, colorize, texturize into either a 3D print or a 3D object that you can view in VR. And we literally have a model right here in the studio that you just received like 10 minutes ago.
Yes, so, I appreciate it.
Do you want to walk us through about how you would use this model?
So this is the model here. So for folks looking, and so this is the model. This is a patient of ours who's going to have surgery, and so preoperatively, you can see it there. So preoperatively, we have our CT scans done. And this allows us to create this model. So they were kind enough to create this model for us. And this is extremely helpful because I can study this model preoperatively to kind of plan myself how I'm going to do the surgery. It also, we can have it in the operating room. So I'll have the model in the operating room, and we'll put it in a sterile cassette bag, and you can then look at it during the surgery to see, okay, so here's this landmark. How does that relate to a landmark I can't see that I need to place the screw in? Okay. So it's very, very helpful for planning, and I think surgery is all about visualization and planning. And so this kind of technology can be very helpful for us for planning, but also in the operating room. And then the other thing we do is we take the CT scans and actually have a company create our rods before surgery. So they make them in France and they ship them here. And so I'll plan my surgery and I'll figure out, where do I want to do my osteotomies? How do I want to recreate the spine? And then preoperatively plan it and then figure out what are my rods going to be like. So I can plan my rods beforehand, the design, and then they can produce those beforehand and ship them to us. And so that saves time in the OR, and it also ensures that I get the correction that I want. So these technologies are very helpful, I think, for getting the right outcome that you're planning for.
I'm just curious, if we gave you the same model, but you looked at it in VR and you could rotate it, do you think that would give you the same level of precision accuracy?
So that's a great question. There are some companies working on that right now. I think it would be very helpful, certainly preoperatively. If you were going to use it intraoperatively, obviously you'd have to have some augmented reality headset for that. Okay. But I do think that is certainly something that is possible. Yeah.
All right. Well, I'm pretty sure we can make that happen. We have the tech and the people here. Well, thank you very much for coming on the show. It's a real pleasure having you here.
Thank you for having me.
And now for the next part of the talk, to close out the clinical, we have a pre-recorded video of myself and Dr. Pedro Ramirez, who is the new chair of OB/GYN here at Houston Methodist. So again, this was recorded last week, so I hope you enjoy it. Welcome back. And now for my next guest, I'm very pleased to have joining me in the studio the new chair of OB/GYN here at Houston Methodist, Dr. Pedro Ramirez. Now, on top of being a world-renowned surgeon, Dr. Ramirez was the PI on the Alaa trial, a phase 3 randomized clinical trial of laparoscopic or robotic radical hysterectomy versus abdominal radical hysterectomy in patients with early-stage cervical cancer. The results of that were published in the New England Journal of Medicine. He's also involved with the Ideal Council at Oxford University in England, and in this role he collaborates with leaders in the field of surgical research to develop strategies to integrate innovative surgical tools to the standard of care practice in patients with gynecologic cancer. And he's here today to talk about the impact of robotic surgery in gynecologic oncology. Dr. Ramirez, welcome.
Thank you so much, Stuart, for the invitation. It is absolutely a pleasure to be here with you all. And thank you for the opportunity to speak about the impact of robotic surgery, particularly in the field of gynecologic oncology. Today, I want to share with you some of the important and key features that are integral to the practice of robotic surgery in gynecologic oncology. We're going to speak a little bit about the program development, and that is obviously very important for those institutions that are looking to explore starting their robotics program. We're going to talk a little bit about the surgical adoption of robotic surgery, particularly in our field now. It's been already a number of years since we integrated robotic surgery in the treatment of patients with gynecologic malignancies, particularly uterine cancer. And I'll talk a little bit more about cervical cancer. As you mentioned, the Alaa trial brought a practice-changing data to our field. Specifically, I'll talk about how robotic surgery has impacted the management of patients with uterine cancer, speak also about ovarian cancer, as well as what we have done now as it pertains to the management of cervical cancer. I want to talk briefly again about the value of prospective randomized trials, and particularly in surgery, and this is obviously critical stemming from the results of the Alaa trial, and then just speak a bit about what are some of the future technologies in robotic surgery. I think certainly as we look at developing a robotics program, it is really essential for there to be institutional leadership and administrative support. And integrating a robotics program, as you know, should not be part of a marketing scheme for any healthcare entity, any hospital system. It shouldn't be about just saying that you have a robotic system, but it really should focus on the impact that this will have on patient care. There certainly should be patient benefit that is driving this integration of the program. There needs to be obviously a core of individual surgeons who are interested in establishing that program and moving it forward. There needs to be access, of course, to the platforms and all of the technology associated with the robotic surgery. And one also needs to accept that at the beginning of any program, there has to be an integration of robotics, but within the frame of a particular learning curve. And that's really very, very important to understand. You know, certainly there should be a focus on targeting specific surgeons. And those are key opinion leaders, surgeons who have distinguished themselves for their minimally invasive skills. It should not be about mass surgical training. And certainly this is critically important for the success of the program, because obviously, ideally, one would want to see good outcomes for our patients. There has to be also a focus on identifying key anesthesia personnel that are going to help drive this program. And the nursing staff in the operating room is critically important as well. And of course, obviously, to standardize the systems as much as possible, the process of integrating that robotics program is very important in terms of standardization across the board. And of course, obviously, always bringing in additional surgeon staff and programs over time to continue growing and developing the program. As you know, obviously, like with any new technology, there are always those who are the innovators, and those are the enthusiasts about that particular technology. At the other end of that spectrum, of course, are the skeptics, the ones that really are lagging behind in integrating that technology. But there's obviously a bell curve, and then typically there is integration of that technology by the majority of surgeons when they start seeing that the results are actually very favorable results. In our field, obviously, robotic surgery has grown as we have seen the industry grow, and of course, obviously, we typically use the Da Vinci robotics technology in our hospital. And just looking at some of the data, it's actually quite impressive. Over 1.8 million procedures performed in 2022, more than 3,000 peer-reviewed articles last year, more than 1,200 Da Vinci systems in just 1 year. Worldwide, there have been over 12 million procedures performed, and certainly it just continues to grow as we see the integration of the robotic system. As we can see, there has been an increasing integration of robotic surgery, not only in general surgery, but also in gynecology. And of course, obviously, urology has been critically important in the integration of this technology in the management of patients in those respective fields. I'll speak a little bit about uterine cancer, where it is the standard of care for patients with uterine cancer undergoing surgery. Generally is the minimally invasive approach, that being laparoscopy or robotics. But really, this technology has really been a paradigm shift in our field. For many years, patients with uterine cancer underwent an open procedure. Many of these patients are obese patients who have other perioperative risks, and certainly the integration of minimally invasive surgery was a revolution in terms of the management of patients with uterine cancer. This was really started by a landmark study, which was called the GOG LAP2 study, that randomized patients with early stage uterine cancer to either open hysterectomy or laparoscopic assisted hysterectomy. And in that study, certainly it was noted that even for very obese patients, the laparoscopic approach was ideal. But more importantly for us, it was to determine that it was safe oncologically, that by implementing a laparoscopic approach, that we were not hurting patients in terms of higher rates of recurrences or lower overall survival. And what that study showed was that, in fact, when compared to open surgery, the minimally invasive approach, at that time laparoscopy, was not associated with a detriment in terms of the outcomes for these patients. In other words, minimally invasive surgery was equivalent to open surgery. So certainly, obviously, this was the first study that integrated minimally invasive surgery in the management of patients with uterine cancer. Subsequently, there was additional data supporting the fact that robotic approach was also a very safe approach for patients with uterine cancer. As you can see here, there were studies that actually also supported that minimally invasive surgery was associated with a decrease in length of stay and a decrease in complications. This one particular study suggested that if minimally invasive surgery was done in 90% of cases in the US annually, there will be over 8,000 fewer complications per year, 127,000 fewer hospital days per year, and over $500 million saved per year. So certainly this is quite a paradigm change for us in the management of uterine cancer. In our field also, we have now integrated sentinel lymph node mapping with indocyanine green. This was the results of a landmark trial called the FIRE trial. And in that trial basically showed us that the ICG technology and the integration of ICG sentinel lymph node mapping would no longer require patients to undergo pelvic or periodic lymphadenectomies, which is associated with a significant amount of morbidity and potential mortality. I'll just share with everyone a video that demonstrates some of the robotics technology in the setting of endometrial cancer. And in this video, one will see that there is evidence of excellent visualization with the robotics technology. As you can see here, we're seeing the uterus with the bilateral tubes and ovaries. And we're now going to explore whether we can identify the sentinel lymph node. And I think everyone can see clearly how the indocyanine green clearly outlines the sentinel lymph node in the pelvis. Here we're using the robotics technology, using the bipolar coagulation to enter into the right retroperitoneal space. And by doing so, it'll expose the sentinel lymph node, which gives us an opportunity to evaluate that lymph node specifically to determine if there is any evidence of metastatic disease in that one particular lymph node. And as you can see here, once we have entered the retroperitoneum, then one can see the lymphatic channels and the point of interest, which is that sentinel lymph node that one can see here is clearly identified with that fluorescent dye. And this gives us an opportunity to avoid doing a full pelvic lymphadenectomy, which was not only time consuming, but also it was associated with longer operating time. It was associated with potential higher risk of complications. And by just removing this sentinel lymph node through this robotics technology, then one can identify the lymph node that has the highest risk for potential metastatic disease. And certainly this is a technology that made it feasible for many patients to undergo this unique evaluation of the lymph nodes to determine if there's any evidence of metastatic disease, and one can clearly see the lymph node of interest in this case. Now, as it pertains to cervical cancer, this is a different story, because in cervical cancer for many years, with the retrospective data, it was shown that perhaps the minimally invasive approach, either laparoscopy or robotics, was very appropriate for patients with cervical cancer. However, this was studied prospectively in what is called the LAC trial, and Stuart alluded to this trial. This is a trial that we conducted, multiple institutions throughout the world, and the trial was a prospective randomized trial comparing minimally invasive surgery to open radical hysterectomy in patients with early cervical cancer. Much to our surprise and the surprise of our community of gynecologic oncologists internationally, we found that with a minimally invasive approach, either laparoscopy or robotics, the recurrence rates were 4 times higher. That's 4 times higher recurrence rates when doing minimally invasive surgery compared to open surgery. So obviously, this was quite an impacting finding for our field. And a number of institutions actually looked at their own data, and this was actually a meta-analysis and a systematic review of over 9,000 patients that evaluated data from numerous institutions, numerous publications. And in fact, from that study, the results were very consistent with the LAC trial, that the rate of recurrence and the rates of death were actually higher with the minimally invasive approach. The all-cause mortality favored the open approach. And the final finding from this study was that among patients undergoing radical hysterectomy for early cervical cancer, minimally invasive radical hysterectomy was associated with an elevated risk of recurrence and death compared with open surgery. So what happened in the United States after the publication of the LAC trial? Well, this was one of the first studies actually that evaluated the impact of just the presentation of that study in a national meeting, the SGO meeting, back in 2018. And as you can see here from the blue line, the study was presented in March of 2018. And just from that presentation, there was a significant decrease in the number of cases that were done by the minimally invasive approach, either by minimally invasive laparoscopy or robotic surgery. And that ultimately led to numerous guidelines. All of the guidelines that are in our field of gynecologic oncology, basically converting the recommendation to saying the open approach was the standard of care for patients undergoing radical hysterectomy for early cervical cancer, and that minimally invasive surgery should only be performed in the setting of a clinical trial. So today, there are actually 3 ongoing trials evaluating robotic surgery to open surgery for radical hysterectomy. This is the first trial, which is called the RAC trial. This is the second trial. This is an American trial, which is actually also called a ROC trial, just by one letter difference, and a trial out of China also comparing the same question, robotic versus open radical hysterectomy. And of course, we're awaiting the results of that study. And then lastly, I'll talk briefly about ovarian cancer. Ovarian cancer usually manifests with advanced stage disease. So typically, most patients need to undergo either neoadjuvant chemotherapy or open surgery. So there's not much data in terms of the approach with robotic surgery to ovarian cancer. We understand that certainly if a patient has what appears to be an early stage, so an adnexal mass, and no evidence of any other disease, then it's reasonable to proceed with a robotics approach. However, if there is evidence of widely metastatic disease, as you see in this figure, then typically there should not be a place for robotic surgery in those patients. I'll highlight the statement from the FDA that certainly alludes to the uses of robotic-assisted surgical devices, and they highlight that while robotic-assisted surgery is safe and effective in performing certain procedures when used appropriately and with proper training, the FDA has not granted marketing authorization for any robotically assisted surgical device system for use in the United States, and specifically for the prevention or treatment of cancer. Many of those who are strong advocates of robotic surgery would argue that certainly there has not been approval for any instrumentation for the use in cancer surgery. So certainly there are those who may not agree with this statement in full. But obviously we go from the past to the present. We have definitely transcended, and now there's obviously many new strategies and platforms for the robotic systems, including a vaginal robotic surgery approach. I will highlight that the ideal collaboration that Stuart mentioned in the beginning of his introduction is a collaboration of surgeon scientists who are looking to explore the evaluation and the integration of robotic surgery into standard practice. So I will conclude that certainly when looking at key elements for program development, there has to be institutional support. Surgeon designation and team development is key to the success of the integration of that program. there has to be a learning curve consideration. And that's really very, very important in order to assure that patient outcomes are safe. Minimally invasive surgery is the standard of care for patients with uterine cancer. Open surgery is the standard of care for cervical cancer. There are ongoing studies, and obviously we're awaiting the results of those studies. For ovarian cancer, the standard is open surgery for advanced disease, and certainly can be used for early stage disease, either laparoscopy or robotics. And then obviously novel technologies must be thoroughly evaluated, and I will refer our viewers to the IDEAL collaboration for further details on that. So with that, I want to thank you all for your attention, for your participation in this program, and I want to thank Stuart for his invitation, and certainly the Houston Methodist Hospital for their support in our continuation of our robotics program.
Okay, thank you, Dr. Ramirez. That was very insightful there. Good time for a few questions. So you've been here for about 4 or 5 months now. So what are your future plans here at Houston Methodist Hospital in terms of building out a robotics kind of program?
Yeah. No, I think obviously it is important to continue to emphasize the benefit to our patients of not just robotics, but minimally invasive surgery. Obviously, it is extremely important for us to continue the evaluation and training for our young faculty and our trainees, our residents, so that they will be able to carry on that particular component of their surgical armamentarium where they're graduating. So obviously we're continuing to expand our training, not only in the simulation lab, but also in the operating room. We continue to emphasize the importance of, obviously, all the steps of that training, continuing to spend time in the laboratory, watch videos, and then follow through in the operating room. We want to ideally, of course, obviously continue to recruit faculty who are very proficient in not only robotics but also laparoscopic surgery.
So you're talking there about training, actually using physical robotic systems, but do you see a space for maybe augmented reality or simulated robotic systems that are easier to get access to?
Absolutely, absolutely, and that's an excellent point, because I think that traditionally we have been used to the training actually going to a laboratory, and that can be incredibly costly, time consuming, resource consuming, and I think that as we are seeing newer technology, it is becoming a much more streamlined, where you can obviously many times use your laptop, you can use your phone, your tablet to integrate into that training at any point during the course of your residency program or the fellowship program. So it's really exciting to see the unique technology that is being developed for training.
And you mentioned as well, I think in your first or second slide, you need access to platforms. Now, are you talking about specific robotic platforms, or what type of platforms?
Yeah, I think certainly when we look at what we're doing as an example with the IDEAL Council is that we're evaluating how is it that we can provide a platform so that robotic surgery can be integrated safely into the practice of medicine. Certainly as I'll give you an example in the field of medical therapeutics, as for example in chemotherapy, that performs the first robotic whatever procedure, and then that surgeon presents it at a meeting, and then everybody that's at that meeting wants to learn that particular approach. And then those surgeons start actually becoming trainers, and they start becoming much more proficient in that approach. Then often healthcare systems and insurance agencies will support it, because that's what the public is asking, that's what the surgeons are becoming proficient. And then it's actually the last step where they say, well, is this the same or better than how we used to do it? So obviously I think that through the work of collaborations like the IDEAL group, that we're able to much more systematically evaluate how do we integrate new technology, not just robotics, but new technology, surgical technology, into the standard of care of patients safely?
I think, obviously 2023 has been somewhat the year for AI,
yeah,
right? we're looking at a lot of autonomous image-guided robotic systems here, and we're pulling in AI and seeing what works for us, what doesn't. So what are you seeing in the forefront of where AI is having a play in robotics?
Yeah, I mean, we see it in so many other industries, obviously including the aviation industry, where the technology is integrated to really definitely improve the performance of the driver, be it the pilot, be it the surgeon. And I think this is really an exciting time where we're seeing AI now becoming much more integrated, where a surgeon may have a much more clear understanding and an expectation of what they're going to find intraoperatively in the preoperative period, because of all of the AI integrated imaging and all the tools that have been integrated into a platform that tells the surgeon this is how the tumor conforms based on the anatomy of that organ, on the anatomy of the vasculature around that organ. And it's really exciting to see some of these models that basically mimic exactly what you find intraoperatively.
No. Yeah, do you think it'll get to the point where the AI is so advanced that it becomes completely fully autonomous, and you're more of a kind of like looking behind the shoulder of it happening rather than actually doing it yourself?
Realistically, yes. I think there is that technology. I don't think that we're there yet. I think that certainly there's so much value, obviously, for human processing of data, immediate processing of data, and obviously attending to potential issues or complications. So I don't think that, at least I don't see it in my lifetime, where the surgeon will be completely, absolutely excluded from the surgical procedure. But I can certainly see that there is the potential for a significant amount of technology-driven surgery and surgical approach to our patients. And in fact, that's not a bad thing. I mean, I think that if it proves to be safe, and perhaps even safer, I mean, if you're integrating this type of technology, it basically reduces distraction, it reduces fatigue, it reduces so many of these other elements that could impact on the outcome of that surgery.
Correct. Well, let's see where we are next year with that. Okay. Dr. Ramirez, thank you very much for coming on the show. It's a pleasure to have you here. And thank you. So we're now in session 2 of the symposium, and we're focusing on immersive and augmented reality technologies in healthcare. My first guest on the show is Nico Charles from Verizon. He's going to be talking about practical transformation of 5G enables XR in healthcare. Nico, pleasure to have you on the show, sir.
Thank you, Stuart. Thank you so much for having me, and thank you to Houston Methodist as well. It's a real privilege to be here to speak to everyone.
So where are you streaming in live from, just so we know geographically?
I am from the sunny city of Seattle, where it is cloudy and pouring rain, and it will be for the next 4 or 5 months.
Well, we have a little bit of rain here in Houston, which we really need, so that's good stuff. So I'd love to hear about what you guys are working on, Verizon, what you're bringing into the mix.
Absolutely. Let me share my screen here. All right. So my name is Nico Charles. I run a product innovation team at Verizon focused on building enterprise solutions at the nexus of XR and 5G. But I'm sure you have some burning questions, and while we'll have QA at the end, I wanted to hit a few of these questions right off at the top. The first being, why is there a Verizon guy at a healthcare conference? Isn't this a giant waste of my time, and should I join in the next 20 minutes when the really important stuff begins? And if your 5G network is as good as you say it is, can I just turn it on, forget about it? Do I really have to talk to you? And the quick answer to those questions is Verizon is really bringing the network and an edge compute solution, which really is an integral part of your training, your simulation, or your clinical solution. But I'd like to take a step back and just give you Verizon's perspective on XR and 5G in healthcare. And that is that we live in a flat world. And I know there's some medical professionals, some scientists, some engineers in the room, but the fact of the matter is our primary interface with technology is 2D. We look at 2D content on flat screens. Think about your phones, your tablets, your laptops, PCs. Primarily, we have a 2D relationship with technology and with compute. Now, that is beginning to change, and we are on the cusp of moving into a 3D world with 3D and spatial computing. And XR is going to be the lens through which most of that 3D and spatial computing is experienced. And let me take a moment. I should have defined this earlier, but my team defines XR as anything to do with augmented reality, virtual reality, 3D content, and spatial computing. And there are other adjacent technologies that we leverage, but that is the core of what we focus on. So with that, I'd like to take a moment just to talk about convergence. And the convergence here that I'm referring to is the convergence of AR and VR. So today, AR and VR, we typically think of separately. We have different strategies for them. We largely experience them on different devices. But AR and VR are converging, and it's really just a matter of moments before we will no longer distinguish between the two, and the device or devices that we experience them on will be a single one with modes for one versus the other. And there's evidence of that out there today. The Magic Leap 2 has a dimmer function, which is essentially an AR or VR mode. The number of VR devices that have increasingly improved pass-through video, including the recently announced Meta Quest 3. And probably most strikingly, when Tim Cook announced or unveiled the Apple Vision Pro, one phrase he didn't use in his entire presentation was virtual reality, because Apple's inspiration is for an AR world, an AR experience. It's both on the consumer and the enterprise side. But make no mistake, the Vision Pro is a VR device. At Verizon, our focus is primarily on AR because that's where we see most of the impact. But everything I'm going to talk about applies to both AR and VR and other holographic displays. So with that, I just want to take a moment to point to the evolution of enterprise-grade AR glasses. Back in, I believe it was 2014, the original Meta, before Facebook and Zuckerberg took over that name, launched the Meta Developer Kit 1, and followed that up quickly in 2016 with the Meta Dev 2, which is our first real glimpse at the possibility of wearable AR in terms of mass market reach. Microsoft followed that up with the launch of the HoloLens 1, and then in 2019, the HoloLens 2, which is the device that most of you are probably most familiar with in your training and clinical applications with respect to AR. And it's an excellent device, but is several years old now. And there are a plethora of new devices coming on the market. but the DigiLens Argo is one particular standout because it has all of the capability of the HoloLens 2 and many greater advantages in an eyeglass form factor, excuse me. But this is just the beginning because purpose-built devices are right around the corner. So the possibility of AR, the future of AR, it's really here now in many respects. So what does 5G mean for XR and XR development in healthcare applications? Well, for any of you who have been deploying any of you who have been deploying XR applications, either on the training and simulation side or on the clinical side, you're likely bumping up against limitations. And those are limitations around these components that you see up on the screen. So fidelity of content, jitter and holographic drift, spatial anchors and positioning, the number of simultaneous users who are truly sort of interacting back and forth as opposed to just bystanders typically maxes out at around 2 to 4 or 3 to 5. If you're an IT department or a facilities person, the secure deployment of these experiences over Wi-Fi is a giant headache. And real-time capabilities are just on the edge of truly being production ready on today's networks. But these are all capabilities that 5G and edge compute either solve for or significantly reduce the problems and limitations associated with them. And what we're doing at Verizon is building XR APIs, both building and leveraging ones that are out there from application providers and putting them on our edge and optimizing them for 5G delivery. So what does that actually mean in practice? I'll give you a few examples. It means photorealistic experiences are just around the corner. And the limitations there are no longer with the network, but likely the optics on the device. It means that compute, whether CPU or GPU, can be moved from the local device to the cloud. And the cloud can be on-prem. It can be a server rack somewhere in the hospital. That means elimination or reduction of equipment in the OR or in places that need to be highly managed. If content is streaming to devices instead of downloading, it means that management of that content can happen centrally. So if you have privacy, PII, or security concerns, which all of you do, it means that management of devices becomes much less of a headache because content is streamed from a central server and managed centrally. Lastly, it turns out 5G works both indoors and outdoors. So this doesn't just mean greater mobility for equipment, but also for processes and enabling sort of true 3D 6-DoF remote assist for field medics, for EMTs, enabling just-in-time training that just wouldn't have been possible in the past. So let me give you an example of one of the things that we have done. Excuse me. So Project Convergence is a collaboration with the VA and more specifically the National Center for Collaborative Healthcare Innovation at their hospital in Palo Alto. And we've worked with the VA and with Metaviz and Microsoft. And I'm not going to describe Metaviz because Dr. Morley is coming on next, and surgical AR is an incredible solution that he's going to describe. But we've worked with these companies in the VA to build and enable the first 5G equipped hospital in Palo Alto, and we're deploying the MetaViz platform and software solution of surgical AR over a private network. Now, this is sort of what that looks like from a simplified network architecture perspective. The surgical AR application is running on our edge, which is on-prem at the hospital, and that application compute is streaming back and forth to the AR headset, which is connected to, as a temporary solution, to a tethered 5G phone or 5G dongle. All of this is happening directly over radio, cellular radio, which means we are bypassing Wi-Fi entirely and taking full advantage of edge compute's high bandwidth and low latency, ultra low latency on a privately managed cellular radio network. So really the way to think about this is less of an architecture diagram and more an example of a platform of any applications that you can run either on-prem or in the cloud to enable all of those APIs that I showed you earlier on an AR headset, AR glass or VR headset or what have you. So, excuse me. So just to close the loop on that one, with MetaViz and their surgical AR application, which I can't say enough about how amazing it is, we are actually eliminating the need for this cart to have to be rolled into the OR. And you can probably see on the cart, there's a HoloLens 2 headset, and that's the only device that needs to be in there because all of the compute now is moved to that on-prem server. With Level X, which you will hear from Michael Coyne shortly, they are essentially putting a sim center in your pocket with their interactive training solutions that are CME accredited. But they're currently limited in what they can build by the 4G network or Wi-Fi network because there are many interactive training modules that require considerably lower latency. So we are working with them to develop a library of content that requires the low latency of 5G. And then lastly, MetaView and their recently approved FDA approved XR90 system. You'll hear from Mina Fahim shortly. They're doing amazing things, and I wish I could tell you more about what we're doing, but I can't reveal all of our secrets, so you'll have to stay tuned and wait and see there. But I want to point out that these companies I've had the privilege of working with all of them, and there's so much innovation happening because of what they are doing and what they are driving. So they are referring to one of the previous speakers' slides. They're moving from innovation and early adopters and proving out that these are practical applications that can be used today. So I want to just end with this statement of there's so much that XR can do for training, for simulation, and for clinical procedures. And we're seeing evidence of this everywhere. And the amount of data and studies that are confirming this is tremendous. And my ask of all of you is do everything that you can to move these solutions along in a responsible manner, because better patient outcomes are something that we can all bring to bear with the intersection of these technologies. Thank you.
Well, thank you, Nico, for that really great overview and great insight there. I want to show our users exactly what we're facing here at Houston Methodist. If you can play a slide here. So this is us at Mighty. It's our 39,000 square foot simulation center, and we are running a VR demo. It's the VR demo we're using is Mightyverse, and that is our own flagship VR product. It's a metaverse for medical innovation. But what you're seeing here is 5 members of our staff in the Mightyverse. Now, guess what? Guess what the first issue was that we had? It was Wi-Fi kept dropping out. I mean,
Yep.
So I would say to our users, our viewers, etc., if you want to master the art of patience, right, as a personality trait, go into giving VR demos. It will force you to be the most patient, calmest person on the planet. You have to be. There's so many bugs, glitches that come up. So you can develop personally from that. But again, I truly believe that it's not until you start really pushing out XR-based demos that you start encountering the problems that need to be overcome with 5G. Would you agree with that comment? Maybe elaborate a little bit more?
Absolutely. And unfortunately, there's still a great deal of work that we have to do to sort of educate pioneers such as yourselves and others that 5G and edge compute can solve these problems that you are facing. That sort of edge compute platform running over the 5G network means that you can dedicate bandwidth to and prioritize bandwidth to all of those users. That they can have a dedicated connection for each of them. That you can prioritize what one user is experiencing versus another, so that a doctor who is a surgeon who is in the middle of an AR visualization and surgical navigation procedure, their traffic is prioritized over the doctor in the next room who's downloading the latest episode on Netflix. But beyond that, it means that the devices are going to change. The way the applications are built is going to change to take advantage of this greater compute power, to have headsets and glasses that are thinner and lighter. It's all there today. And these companies that you're all going to hear from soon, they're demonstrating that in the moment. And I guess the point that I really want to emphasize is this is not the future. This is happening right now. So this is not pure innovation. This is somewhere in between the sort of early adoption and majority adoption that I believe Dr. Ramirez showed earlier.
Got it. We're pretty much out of time, but in 10 seconds, define to the audience edge computing. 10 seconds.
Edge computing is essentially, sorry, I should have done that earlier, a rack of servers or a server or two that is as close as possible to where the compute is taking place. In this case, it would be servers in a server room at a hospital that are feeding the compute that is happening in an OR on a VR headset or a AR glass.
Wonderful. Well, Nico, again, as always, pleasure seeing you, and look forward to hearing from you again soon. Thank you very much.
Thank you.
Okay, so now for my next guest, we have Dr. Christopher Morley, who is the CEO and co-founder of Methodist. And you may have heard there that Nico kind of introduced them and elaborated on a little bit more, but we're going to hear it straight from Methodist themselves. And the title is Augmented Reality in Surgery Towards a Standard of Care. Chris, pleasure to have you on the show.
Pleasure being here. Thanks for the invite.
All right, over to you, sir.
All right, let me just share my screen here. So this is pretty video intense, so let me know if there's any issues on your end.
Will do.
Cool. So, excited to, in the next 15 minutes or so, just give an update of who we are, what we're working on. It's incredibly exciting. We're really heads down. And I think not just for us, but for the entire field, things are really starting to turn a corner in terms of viability and this being ready for prime time, so to speak. And I think that's a little bit of what I want to kind of share today, just kind of open that up. And when we think about what augmented reality is, we do think about it as a new way of thinking, just at the heart of this, about a new way of thinking with patient-specific data. How can we leverage that data at the point of care? And it is a complete new shift in how we prepare for surgery, but ultimately how we're going to perform surgery. And I think for this audience, I think we're all on the same page about that. And just a brief overview of like some of the people on our team. One of the things I'm personally most proud of is our team, the people that we've been able to assemble over the past 7 years from when we started doing this. And it really is this incredible collaboration of PhD level computer scientists that have done, in their own right, 5-7 years of computer science for augmented reality for surgery. And when we started the company in 2016, that didn't exist. So what you're looking at here is really the first cohort of computer scientists that are dedicating their entire career to this field. And then it's something special happens when you connect that type of person with really proven industry veterans like Kevin Kennedy and Carmen and Diego, who joined us directly from Microsoft on the HoloLens team after amazing contributions there. And then, when we have people like Amy, our regulatory lead, who is at Magic Leap and Stryker, and Katerina joining us from, Butterfly, we're starting to build this incredible nucleus of a team of people. Overall, we're about 30 people in size now, and I think we're just getting started. And I think really most of what I'll show today is neuro-oriented for neurosurgery. That is kind of the tip of the spear of what we started with, but there is incredible overlap to all the adjacent fields that we could talk about. So this is really just a microcosm of the problem that we're tackling and the value proposition of what AR offers. And so there is, one of the most common neurosurgical procedures that is done at the bedside is EVD placement. And, depending on what you cite, it's anywhere 20 to 40% of misplacements of this catheter, largely because it's done without computer-assisted guidance whatsoever. It's done at the bedside, oftentimes in emergent situations. It's a life-saving procedure. And the standard of care is to feel external landmarks and essentially blindly hit an intended target. And that's, when we were looking at like the signal to the noise of like, what are some use cases that we could build a solution that ultimately could make the argument that this should be a standard of care, this rose to the top of that list for us, among others that I'll talk to. And so what this looks like, this was patient 0, basically. So this was about 18 months ago at this point. And this is what you're seeing here is in the emergency room in Bellevue Hospital, being able to place the EVD with AR guidance in real time, and built inside of a real workflow, being able to do this with incredible fidelity. And then ultimately on this post-op imaging, just showing the fidelity of this perfect placement of the EVD. And this is when we got really excited because there's still a long way to go in terms of refining things and usability and this type of stuff. But the system worked. And I think that is what kind of de-risked this entire idea for us. This is what we raised our Series A around. And I think that's really what we're galvanizing around. And I think what's starting to happen now is we're doing clinical trials with this stuff. And what we're finding is a 5x improvement in the placement of the catheter tip to the current standard of care. And that's something we're incredibly excited about. And the top row here is the control arm of a study that we're doing right now. You could see in some cases we cross-court, we start on the left side of the brain, we end up on the right side. This particular case was in the thalamus that needed revision. The bottom row is AR guided using our system at bedside. Here you can see this big subdural hematoma along the left lateral convexity here. And there's midline shift, the ventricles are slit-like, and we're still able to hit intended targets percutaneously with incredible fidelity. And I think that's a big part of kind of what motivates us every day. Because again, we just see this one use case is just a microcosm of what's going to be possible across a range of specialties and procedures. And so what we're doing now is we have the hardware that we deploy. It really comes in two flavors: a pro unit, which is living most commonly in the operating room, and then another smaller unit that's really for like ICU navigation for bedside. And what we've done here is we've combined a very seamless IT integration, being able to pull data immediately by just searching for a patient, pull their data, select the study that you want, out pops a hologram in 10 seconds, and then photorealistic rendering on top of that. And then how do you now register that to the patient and actually conduct the procedure? And so the first thing I'll just touch on just very briefly is photorealistic rendering. And we're excited about this. We continue to push the limits of computer graphics because we think, A, it's just visually stunning, and B, there's something about just delivering the highest fidelity possible graphics that is on the frontier of computer graphics. And so, we're basically doing real-time path tracing. This is just a look of, the SMA and the branches here, left coronary artery and the branches internally thoracic, the circle of Willis. This is something in its own right. We're deploying this on traditional conventional monitors, but it's kind of stunning in its own way. And I think it's provoking a lot of people in terms of even stuff for patient engagement and stuff, stuff like this. Like when you can just visualize this with a fidelity like this, it has a lot of implications. And then I think most of what our team is focused on is really the advanced computer vision of what happens when we put a device like HoloLens 2 on the front of our own face and we're at the point of care trying to help someone. And I think one thing just to remind everyone, like the sensor array on this device, we look at these color videos all the time, but that's just a small sample of what the HoloLens can see as far as the sensors that are on board this device. And so when you think about the camera frustrums and the field of view of some of these sensors, it is much wider, and you have stereo vision in some cases. So what can you do with this? And so we really are pushing the limits of what is possible with the fidelity of the tracking. In this case, like infrared tracking, being able to track new and really limitless amounts of fiducial markers and trackers, having sub-millimeter accuracy, which we've proven time and time again. We're publishing a paper on this in collaboration with folks at the VA. Whatever it is, we're going to be able to basically turn it into a trackable instrument. And I think that's where you can really start to play the mind game of if we assume any incremental improvement year over year, where this technology is going to go. I know there's a theme of this talk around robotics. We do have a robot in-house. We're using it primarily for calibration, and so we can remove all other variables as we're testing our computer vision algorithms, whether it's advanced filtering techniques and just latency, and even the calibrations of the HoloLens device, and finding like very minute, like sub-millimeter errors in the inter-sensor calibration of these things that we can then correct for with software by calibrating some of these things. And then because we have computer vision like this, what we can do now is we could do things like this, where we could track a probe and now digitize anyone's anatomy, whether that's external markers, whether that's bony markers that are exposed, whether it's something in the spine, whatever it is, we can start digitizing this stuff. And then what you can do once you digitize it is you can now use that to do matching. So in this case, we're going to do a surface match of, call it 600 points with the preoperative data, and just have the data snap on with incredible fidelity. And I think this is where we're talking about the usability of this stuff starting to truly hit a new gear, a new level. And I think a lot of this is like just continuing to push the limits of this. So what's easier than a trace-based registration? Well, of course, automatic registration. And so what does that look like? And so just as an example, so here you have a CT scan on the right, all the surface normals of the geometry of the scan, the skin surface, and then the fidelity of the digitization that we can get using the sensors on board a commercial AR headset. So of course this is enough data to do a point cloud fusion, right? And so this is just a video showing the first time that this worked, where we're basically doing this using 3 consecutive machine learning algorithms in a row, where we labeled 30,000 heads from all different orientations and all the feature points. And again, just the fidelity of this as you're moving around, the combination of SLAM technology meeting, coupled with a reference marker. So even as the patient moves, the hologram stays put to them. This is where the usability does become 5-10x better than the current standard of care, right? If you can just walk into a room, like in now when I show this in real cases here, and just walk into the room, select the study that you want, look at the patient, digitize their anatomy, the data snaps on, and you're ready to go. The conventional systems are still setting up, right? And that's where it needs to get to this point for people to take this technology seriously. And I think the rate limiting step in a lot of cases for us now is people seeing this with their own eyes, and kind of re-educating people maybe that have been burned in the past of seeing lower fidelity experiences, what is possible here and now. And so this is just some more case footage. I see a little feed that the videos that I'm playing are running poorly, which is a shame, but I'll share this stuff on YouTube. So this is just a look. Some of these use cases we're talking about are really out of the box, really low hanging fruit. Like in this case, this is a mapping of the STA, the superior temporal artery, and what the name of the game is, like, where is this blood vessel? And so if you're trying to think about like what are use cases for this technology, a really simple one that applies to everything: where are the blood vessels? Just where are they? Because in almost all cases we have a CTA or an MRA just sitting in the server, not being used. And now we could just leverage that data at the point of care and then just grab a magic marker and just draw the branching pattern of the vessels. These are things that we're doing normally, but in things like breast cancer, for example, we're using the radiologist report and we're reading line by line, using written word to describe branching patterns of vessels. And these are things where I think, like, retrospectively, as this improves year over year, we're going to look back at that and just kind of can't believe that's how we did some of these things, because you're going to have tools like this. You're going to be able to just see the answer. And then, this is just whether it's vascular, whether it's congenital stuff, whether it's oncology and tumor sections, and where are the tumor margins, and how do I position the patient, in order to get the best exposure with minimal impact. These are things that, again, are just really out of the box now. And I think it is a whole new way of thinking about what we can do with patient data in many different modalities and specialties. And to that point, another major aspect of kind of just really a natural pairing and natural marriage of technologies is, of course, like a wireless head-mounted display and a wireless ultrasound. And so we're really pushing the limits of this field as well. We have this at a few sites now. We're going to roll it out in a wider array, probably end of this year, early next year. But there's just the ability to just pick up a wireless probe, put it down, immediately you have it pair with the system, and then just have, again, because we have the computer vision and incredible tracking to be able to do this, the fidelity that you can have, and just see the data situated in situ ultrasound. Now that you have this, of course, you could think of this as a paintbrush of data. We are tracking the probe, so now we could literally paint in the data. And what we're doing here again is we're using the robot again to calibrate and really remove variables as we're developing this stuff, and tinkering with all the different algorithms, to just get every single millisecond and every single pixel as correct as possible. And so what we're doing is, and this is where, like, the network of this stuff is just critically important, we're being real scientists about this stuff. And I think that's a big takeaway, is just the depths that we're going to try to figure out the core building blocks of this technology. These are big commitments, and they're going to unlock entire fields and new ways of treating patients. And I think that's one of the most exciting things. And
hey, Chris, I just
yeah,
need to ask you, we're almost out of time.
Yeah. Yeah, the last thing I'll just show you, of course, is just a big umbrella concept of virtual monitors, right? So here, being able to just grab any monitor-based platform and stream that into a wireless AR headset so that you could ergonomically put monitors wherever you want them at whatever size you want, right? These are ideas that they're not secrets anymore. It's just a matter of how do you do it with the best fidelity and in what areas do you drill down into? And I think, these are things that we're incredibly excited about. And I think, again, we're focused on neurosurgery right now, but we're actively deploying this in interventional radiology and ENT, orthopedics, urology most recently. Yeah. So I think there's incredible extensibility to this entire platform that we're building, and we're excited to have conversations with anybody that wants to build this with us. So with that, thank you for your time.
Thanks, Chris. That's truly fascinating. Got like 20 seconds left, right? So regarding all your FDA approvals, etc., what is your intended use for this product?
So the first sentence of our intended use is visualization and manipulation of medical imaging data and other healthcare data, purposely as big and broad as possible.
Okay, so it's across...
subsequent FDA clearances are going to be for stereotaxy, and open up billable pathways to this, to reimbursement.
Okay, so it's across multiple specialities, right? It's not just for one.
Yeah, of course.
Okay, and the final thing is, just so I got this right, are you guys like a software as a service product? It sounds like you are.
That's right.
Okay,
that's perfect. Right. Yeah.
Okay. Well, listen, thank you very much for patching in. It was really insightful to hear what you guys are working on. I do appreciate it. Thank you very much. Speak to you soon.
Okay. Talk soon. Thanks.
All right, so we're still on the extended reality train. There's some really great tech out there. Next title, or next talk should I say, is Streamlining Surgical Decisions Using XR and Medical Imaging. And this is streaming in live from France with our representatives from Avatar Medical. We have CEOs, CTOs, and co-founder Elodie Leitzerman, I believe, and Mohammed El Berry. Guys, welcome to the show.
Thank you so much for the invitation today. It's pretty exciting to see all this innovation around surgery, from robotics to visualization. So yes, I'm Elodie. I'm the CEO and co-founder of Avatar Medical, and I'm here with Mohammed, the CTO. So today we're going to talk more about what we do. Avatar Medical is a spin-off company from prestigious research and hospitals in France, Institut Pasteur and Institut Curie. And we are based in Mountain View, California, and in Paris, France. So we developed medical imaging software solutions for surgeons, leveraging...
Just to make sure, guys, are you sharing a presentation? Because we cannot see it. I want to make sure we're seeing your slides.
Okay.
No.
So hold on. Can you see it now?
Yes. Thank you very much.
Okay. Great. Okay, so so we basically, when surgeons need to plan what to do in the OR, they need to review the images of their patients, the scans, or their MRI. And currently, what they have at their desk is mostly this type of viewers. So slides-based radiology views, and from that, they have to figure out what they're going to find in space. And as Dr. Saifi previously said today, surgery is about visualization and understanding 3D. And what we want to do is to replace this type of experience by something much more intuitive. So we would take the same DICOM data and create a patient's avatar live at scale that the surgeons can navigate into. So we will keep all the pixels and create these volumic renderings so that you can see soft tissues or whatever you need to see and navigate into the image. So of course, what you see here is not really doing justice to a stereoscopy-based experience, but this is more or less what we do. So you might say here, okay, she was totally exaggerating. We have much better than this slice-based viewer to plan what we want to do in the OR. Yes, of course. So you have this 3D image software available maybe through your PACS or maybe on radiology workstation. But all of them, they tend to be super complicated in terms of user interface for surgeons. And they also tend to stay in radiology department. And also what was previously mentioned by the Verizon person. So they are flat 3D, they are projection on screens. And this is definitely not good enough for surgeons. So we have seen also earlier today, but by Dr. Saifi, the usefulness of 3D printed model, pre-op model, and the existence of these models. And today, this is $500 million market worldwide, this pre-op 3D printed. It's kind of demonstrated the need for this perception of depth in the image. So leveraging, the same need, there are a number of competitors of ours which have tried to develop a solution leveraging VR or XR, but using methods based on segmentation, so the contouring of organs and structures, which is kind of nice because it simplifies sometimes the image and understanding. But this will, as a consequence, often take a long time to get the results because you need the images to be sent out somewhere to be processed and get your model back. And you're going to be dependent on the quality of this segmentation, whether it's done by an algorithm or a human. And in any case, when you have your segmented model, then the details are lost. So what we want to do is to deliver to surgeons high fidelity 3D patient-specific visualization in real time, where they need it and when they need it. And so this is how it's going to work. So we have a product which has been cleared by the FDA earlier this year. So it's installed on a computer. You're going to launch the software. You're going to select the dossier of your patient in your PACS because it's connected. Then in a few seconds, what you see here is totally live, the real time. You're going to select your series and you're going to have an instantaneous rendering of the image. From this rendering, we have this patented tool where you're going to select the zone that you need to see in the image on your 2D slice. So here we're going to select an aneurysm and you're going to click on it. And one click, the filter self-adjusts and you're capable of seeing what you need to see in 3D using the flat 3D interface we provide, but also in one click, you can launch a VR session to explore the same data. Then you're going to wear your VR headset, take your controller, and navigate the image in space with a perception, of stereoscopy, so a real perception of depth. And it's seamless and it's fluid, and you can really dive into your data and look for what you need. So it's a volume rendering, so we keep all the pixel and all the information. And as a consequence, it tends to be superior to visualize soft tissues. And as a consequence, we have been having a lot of traction in the surgery field where soft tissue matters. So oncology is a big one, the question of the margin of the 3D environment. Orthopedics procedure for which soft tissue matter, so can be muscle, can be nerves, can be tendons, and also in cardiovascular, basically for procedure where segmentation is not working so nicely. So you can see a number of names which may sound familiar to you. So for instance, we've been doing cases in breast cancer surgery at Cleveland Clinic. We published some of the cases we've been doing with University of Massachusetts also for breast surgery and reconstruction earlier this year. And I'm going to present you in details 2 studies we've been doing with 2 hospitals to showcase the impact of this type of visualization on surgery decision-making. I want to mention that this type of tool is also super useful for medical education. And so to teach, pathological cases to students. And now we have a number of customers, so CUNY in New York and in Europe, where the solution is deployed for education application. So I'm going to now talk about the first study, which we did at Rush University in Professor Kolzman's team for pelvic sarcoma surgery. So if you look here at the image on the right, you can see this huge sarcoma and you need to understand the involvement of the sarcoma. And then you can see that, you know, in the same viewing experience, you can switch to the soft tissue, to the bone visualization, because this one-click filter tool that we have is also available in VR. And you're going to have also the possibility to relate what you see to radiology views, which you have corresponding in the scene in the bounding box surrounding the model. So we have looked at cases that Professor Coleman's team has been working on in previous years where there were failed resections. So 4 images that were reviewed by 5 surgeons, so 9 reviews total. And previously with their standard tool, for all of these cases, surgeons thought that they were not understanding the tumor borders clearly. While in 6 out of 9 reviews, they were thinking, you know, they would understand clearly the tumor borders in Avatar. Also, generally speaking, this type of viewing experience is delivering a better understanding, as reported by surgeons in the vast majority of cases. They also think they have a better understanding of measures and volume, and a majority is also more confident in their surgical planning. So this was an example in oncology. We have a publication in preparation that's going to come later this year, we hope. So we have another application in vascular surgery in which we have benchmarked the tool Terra-Recon of Aquarius, which is a flat 3D solution for vascular with Avatar Medical. So in this tool, you know, you can crop only using radiology planes, while in the VR experience we provide, you can crop whatever direction. You're going to interact with your model only by rotation with your mouse, while in Avatar, you can use a 3D controller and really manipulate it in any direction in space. And you have the possibility to simply relate what you see with these radiology views that you have available in the VR field and that you can review simultaneously with the model. So in this study, we wanted to know if this stereoscopic view versus a flat 3D view had any impact on surgical decision-making. So what we did is that we had surgeons review cases of visceral aneurysm surgery, first using Aquarius and then Avatar, and then we were asking them questions about image analysis and surgical decisions, and then we were recording whether they were changing their mind. So we had 10 surgeons participating, senior, juniors, and they were reviewing 10 cases and 29 reviews were made total. What's kind of fascinating is that in 7 out of these 29 cases, the surgeon counted a different number of efferent branch from the aneurysm. In the cases where they counted a similar number, 22 cases, in 6 cases, they made a different decision about the branches they want to sacrifice or not. So, and in 4 out of these 6 cases, it was to sacrifice less branches. And maybe the most fascinating finding of this study is that for 4 out of these 29 cases, the surgeon changed his mind about the best surgical approach for the patient between an endovascular surgery and an open surgery. In 3 cases from open to endo, and in 1 case from endo to open. So, you know, we also have the hope that this type of stereoscopic VR-based reviews are going to ultimately, at the end of the day, promote less invasive surgery and then possibly better outcomes for the patient. In the study, we also asked the question more qualitative about the perception, and we kind of found the same type of results. You know, in the vast majority of cases, surgeons were reporting that they had a better visualization of the aneurysm, of the branches with the VR stereoscopic visualization. So now I will let Mohamed talk about what's coming next in our pipeline besides this first FDA-cleared product.
Okay, great. Thank you, Elodie. So, yeah, I'm going to spend the last few slides of this presentation talking about where we're going with our technology. One important point that we want to mention is that while we seek to democratize the understanding of medical images, we also want to democratize the use of our technology. And one of the things that we've been working on for the past while is to develop an ecosystem of technology components of our solution to make this more accessible to different types of users, which can include medtech companies and hospitals seeking to develop specific solutions. So we're developing this module-based ecosystem based on API communication to allow for this easy kind of plug-and-play integration. One of the important reasons, the pretext why we decide to do this is because we are aiming for cloud deployment. I mean, we're actually working on this with one of our current medtech customers. And the idea is, as Elodie mentioned, is to make our solution available where surgeons need it and when they need it. So in principle, on any, we're decoupling ourselves from the hardware requirements. So one interesting topic that arises from this is the possibility of doing a cloud XR. So for this, we're investigating solutions related to augmented reality and virtual reality streaming. So this, I don't have too much time to go into it now, but I'd be happy to take a question about it. But that is one of the main drivers. With regards to the ecosystem that we're developing, I'm going to spend the last couple slides just talking about two main core components. The first of which is related to this idea of doing organ detection, this AI-based organ detection. So while our technology, our rendering technology, does not use segmentation in the classical sense, segmentation is nonetheless useful when we are developing very specific clinical applications where we need a firm understanding of certain anatomy and certain structures within that are visible within the images. So what we've developed is a pipeline where we can integrate different types of AI models to interface with our solution. The idea is that we develop our own AI models ourselves in-house, but we will also open this up to partners to integrate their own models. So this is something that's very, very interesting for us, specifically in the development of these clinical applications, which we're also working on. One last point is that the visualizations that we have related to segmentations, they're meant to complement our current volumetric visualization that we're developing and that we are building upon in the second technology component, which I want to talk about, which is what we call the Aperture engine. It's our next generation rendering technology. We saw in Chris's presentation this idea of doing cinematic rendering of volumic data. Siemens, with their cinematic rendering software, can do similar things. We are in total agreement. This type of realistic, photorealistic rendering can help surgeons, the better understanding they have of the 3D, the 3D data when visualizing in stereoscopy. Couple this with this photorealistic, ray trace based rendering can only add to this experience and facilitate the experience for surgeons. However, it needs to be streamlined. It needs to be easy to access and easy to understand. And that's the motivation behind the semi-automatic filtering tools that Elodie had showed earlier in the presentations to make this very simple to use. One of the key components with the next generation rendering that we're developing is this idea of doing a video streaming. So again, we're trying to decouple ourselves from these hardware requirements, which was a theme in some of the previous talks. We don't want to have surgeons to always have to have a gaming computer around with them. So in principle, this rendering technology, it falls in this the same context of doing streaming. In principle, it can run on a mobile phone. And this is also just to reemphasize the point that this is meant to be a separate module that we can integrate in our own products, but also in other products with other partners that we have. So with that, just want to finish with some take-home messages of our presentation. So as Elodie mentioned, we have an FDA-cleared technology that seeks to democratize the understanding of medical images through the use of XR and a very streamlined user experience, which has led to a number of studies. The goal is really to open up the understanding of medical images beyond the radiologist, so they can really, so surgeons, for example, can really take advantage of this data. we've demonstrated that there can be a real impact on surgical decision-making in the variety of clinical studies that we've performed. And what we're seeking to do right now is to get a firm understanding on what effect this has on outcomes. And finally, as I just mentioned, we're using our technology platform to really open up the possibilities of different types of applications, not just limited to XR, but also just pure visualization for different partners such as hospitals and medtechs. And of course, if you have any questions, feel free to contact us. Our email is listed there. And with that, we'd be happy to take any questions that you may have.
Right, thank you guys. I really do appreciate that. You know, got less than a minute for questions, but can you just tell me, so what headsets are your customers using?
So the current product is cleared with the HP Reverb headset, and it's going to be extended to the headset you've been seeing on the video, so the HTC Vive Elite headset.
Okay. And you mentioned there about AI-based organ detection, which I found really, really interesting, and I'm curious, are you potentially want to look at medical device detection as well? You know, like devices that have been implanted that are degrading, that could be kind of characterized, etc.?
That's an excellent question, Stuart. So for that, I mean, the key to the organ detection that we're doing, it's deep learning, and it's based around the types of data that we have. If there's a sufficient number of images where we have these medical devices, this would definitely help in being able to detect such objects. But since the signature of a lot of medical devices, implanted medical devices, is very specific, there are potentially other, non-AI related ways where we can delimit such structures in the body. But it's a very, very interesting question that you ask.
And if I may complete, about the need to visualize some hardware that you're gonna have implanted in a patient. So what's really nice about having this instantaneous rendering is that you can have them from CBCTs or scans done in the OR live. And so typically, if you want to look whether you have put your screws in the right place in spine surgery, then you can do an image intraoperatively. And before you are closing the patient, you have the possibility to check whether this hardware is placed at the right place using our type of visualization.
Got it, understood. Listen, thank you both for appearing on the show. I really do appreciate your participation, and I'll see you soon, okay? Say hi to France for me.
With pleasure.
Thank you so much.
Thank
No
you.
worries.
Goodbye.
Au revoir. Okay, so now on to my next guest. We have a representative from Level X. It's Michael Coyne, and he's going to be here talking about advancing the practice of medicine through the neuroscience of play. Michael, are you there? Okay, I think we're just getting set up. All right. Hey, Michael, how you doing, sir?
I'm great, Stuart. How are you? It's nice to see you.
Good, thanks. Okay, so over to you. Love to hear more about your enhancing your science of play.
Yep, absolutely. Thank you so much for the opportunity to join you all today. We really appreciate it. My name is Michael Coyne, and I am the Vice President of Business Development here at Level X. And so we're going to talk today about advancing the practice of medicine using the neuroscience of play. And so behind me is a reel of some of our technology that's playing, highlighting some of the most interesting procedures, workflows, cases, algorithms that are impacting learners today. And we are the world's leading medical video game studio. And we're able to accomplish this because we have some of the best and brightest from the video game industry who've been working on franchises like Call of Duty and Words with Friends and Madden. And those individuals are working alongside with physician experts. We have over 100 physician advisors that we partner with in order to create the most realistic and dynamic and engaging experiences possible. And so all of these experiences are available to any learner, anywhere in the world, on any device. It doesn't matter if it's augmented reality or virtual reality or the phone that's in their pocket or the web browser that they're using on their computer screen. They're able to have an incredibly immersive experience where they're able to train and get educated on some of the most complex cases that are available today. And so we're super happy to talk to you all today about advancing the practice of medicine through the neuroscience of play. And when we talk about the neuroscience of play, what we're referring to is harnessing the state-of-the-art video game technology and the neuroscience of game design to change physician behavior and habits at scale. So it's all about hitting the right balance of reward and frustration and skill and challenge. And we're able to maximize the dopamine release in the brain, which leads to deeper learnings and increased recall. And it's always all about the why. So why is this so important? The evidence shows that we remember only 10% of what we read and 90% of those tasks that we actually do. So by immersing themselves in ultra-realistic medical scenarios, HCPs are able to get that hands-on experience that they can then apply to real-life patients. And they can do this all in a consequence-free environment. And when we talk about the neuroscience of play and accelerating the adoption of new skills and treatments in medicine, by way of background, it's important to note that LevelX works with some of the top societies, medical device, and pharma companies in the world, as well as extraterrestrially. We work a lot with NASA, as well as SpaceX. And an interesting anecdote, when the Translational Research Institute for Space Health had started to survey the simulation landscape, they had found LevelX as having advanced capabilities in this area, and we're excited to share a little bit more about that project in just a couple of moments. So I wanted to highlight a couple of different aspects, and that's about the reach and the impact of LevelX technology. So one of the ways that we disseminate some of these games and simulations is through apps that are available to anyone that has access to the Google Play or the Apple App Store. So to date, we have over 3 million apps that have been downloaded. We have over 1 million medical professionals that have played through these experiences. And when we've taken some of this content and ported it over to either augmented reality or virtual reality experiences, we have over 10,000 users that have played through those different types of cases. From an impact perspective, we're measuring everything that takes place as part of these experiences. So when we track this information, 9 out of 10 medical professionals showed improved performance. When we look at the pharma companies, we're seeing very significant, script lift within these experiences. Engagement, depending on the complexity of the experience, ranges anywhere from 4 to 19 minutes of engagement, going through the treatment algorithm, going through the workflow, or whatever the experience may be. And we also have continuing medical education credits that we offer through our platform. And to date, we have over 2 million CME levels that have been played. And we've been widely recognized for this very innovative approach with a variety of different awards and recognitions in the industry. And we're expanding that. And we're really excited about a recent announcement that we made about our partnership with the AO Foundation. So LevelX, our parent organization, Brain Lab, and the AO are going to be leveraging all these different types of technologies for a variety of procedural cases, from craniomaxillofacial to spine to trauma education and beyond. And so at LevelX, we know that there's a lot of noise around the HCP. They're being bombarded all the time for their focused attention, whether that's presentations or conferences or new technology. And at LevelX, we're using this technology in order to cut through the noise and really get to the focused attention and have the learner identify and learn for themselves all the different procedural aspects or the content that we're really focused on. So it's about reducing the barrier to entry and getting hyper focused in terms of the educational content and meeting the learner where they are. And in terms of meeting them where they are, it's about making it as accessible and easy to access as possible. So whether it's the phone that's sitting in their pocket, the tablet they're using, the browser that they're working on either at home or at the office, or the virtual reality headset that they may have, any learner, anytime, on any device is able to engage and interact with this content. And so it's one thing to talk about conceptually what we do at LevelX. It's a whole other thing to kind of see it and experience it for yourselves. So I'm going to bring up a demo here where this is an example of content that's available in the Google Play and the Apple App Store. And so I'm going to go to our CardioX experience, and I'm just going to take us back here. And so this is cardiology experience. Again, Google Play, Apple App Store. It's free to use. I can go on the various tabs. When I go to the CME tab, there's a variety of different cases and procedures that are available. So whether it's diagnosis, whether it's treatment or interventional cases, they're all here for a learner to experience, and they vary in degrees of complexity. I'm going to jump into one in particular, and it's important to note that at Level X, while we create these really immersive experiences, there's a lot of design and thought being put into what we're trying to convey. So here we're very explicit that we're focused on the specific target audience for interventional cardiologists in this example, and we highlight the statement of need as well as the educational objective. So what is the learner going to achieve as part of this objective? And then who are the faculty that consulted on this case? So they provided the materials or they provided the case information, and they wanted to highlight this for its educational imperative. And so now when we jump into the actual game, what you see is what you would typically see in a cath lab. So I'm able to move the anatomy around. I can take a puff of contrast. This is all working directly from my cell phone. I can start to, drive through the anatomy in order to treat the calcified stenosis. And when I get there, I can open up a whole pick list of tools. So whether it's balloons or drug-eluting stents or an arthrectomy drill with all the different sizes, we can start to use all this criteria in order to treat the patient and complete the case, as well as get that CME credit. Now, other examples also include what we have in our gastro space. And again, this is just running on my cell phone. This is an example of a solution called GastroX. And when I go into this, it's a little bit of a different look and feel than the cardiology example that I shared previously. So we're presented with a patient, we're communicated the different objectives of this experience, and then we are driving, again, from the device that's in your pocket through the colon. And we have a whole variety of different tools that are available at our disposal. And we have an objective where we're supposed to treat a variety of different polyps as we're going through. And so what's unique about this case is I'm going to grab the forceps. I notice a polyp here. I'm going to start to advance toward the polyp, open up my forceps. Once I am able to pull on the polyp, what's going to happen is that I'm going to trigger a bleed 2 meters inside the body. And so we have a variety of different tools that are available to us. I can choose an argon plasma coagulator, epinephrine, a whole host of different tools in order to problem solve and see what makes the most sense in terms of treating this patient. For the case of this demo, I'm just going to use the argon plasma coagulator till I'm able to complete. The bleeding has stopped. And it's just important to note as well, we do have subsurface scattering of light. This is a completely simulated environment. So the tissue is all squishy, and we can navigate anywhere within the anatomy within this consequence-free, completely simulated environment. Another example of this technology that I want to show is using our cloud gaming technology. And so this is a platform called Remote Play, where multiple learners can jump into an experience together. So I can start to move an Israel retractor and place it at the right-hand side of the knee. And then another learner can come in and place the Israel retractor on the left-hand side of the knee. And we can start to do this procedure together in a virtual environment. And what's unique about this platform is that it doesn't matter where geographically that the two learners are. They can still have a very robust, engaging, dynamic discussion, either synchronously or asynchronously, which means that they can either do the procedure together in a guided scenario, or an individual, as you can see, there's instructions here at the top of the screen, can read the top of the screen, insert the IM rod into the femoral canal, and continue through the procedure in that virtual setting. And this platform doesn't require any downloads. It doesn't require any drivers. It's as simple as accessing via a QR code that I can just put up on a screen that anyone with a phone can scan in and jump in, or using the link where they can access it on their desktop browser or another device that's convenient to them in order to access the experience. So it's one thing to talk about, the experiences and showcase some of the demos. We also are highly focused at Level X on the studies and the results coming out of these studies. And so we wanted to share with you today the impact of a study of a video game that we had created on experienced physicians and their knowledge and practice decisions. And so this is a really interesting study because whereas prior efficacy studies have focused on medical students and residents, this study was really focused on the impact on busy, experienced, older physicians. And so the average age in this study was 45 years old, with an average number of patients of 151 per week and 14 years of average clinical experience. And from a highlight perspective, 40% of those physicians showed improved performance, not only in the game, but when applied to clinical scenarios outside of the game measured weeks later. We also showed that clinical competency increased and that these busier physicians had a stronger affinity to the game than those with lower patient loads. So this is all about that active learning versus passive learning and really finding a way to kind of cut through the noise and engage the learners where they are. We also, as I alluded to earlier, do a lot of just-in-time training for NASA and SpaceX. And so some of the images here on the screen behind me are the crew for the Polaris Dawn mission who are actively using this for training and for performing medical procedures in orbit. And it's this just-in-time training that is critical in ensuring adequate medical care. And at Level X, we also are partnering with NASA for a variety of different ultrasound related activities where with the Translational Research Institute for Space Health, as well as NASA's Institute for Space Health, we are testing the limits of what you can achieve on mobile devices. And so this is an example of our ultrasound simulator that we are creating, where we are, absolutely providing the best in class in ultrasound training to astronauts for these very, critical and significant missions. And as we talked about earlier, it's all about democratizing access to these immersive experiences. So at Level X, when we create a game or we create a simulation, there's a variety of ways that we can make this available through our omni-channel approach. We can put this on a learning management system or within a hospital center's website, where learners on their own free time at their choosing can go in and access this critical information and start to learn about different procedures or scenarios or algorithms in that consequence-free environment. We can also take this content and use it at conferences. So whether that's a trade show or a conference or some other type of learning activity, we're able to create these really advanced, dynamic, engaging solutions in this type of setting to drive scale and to really drive audience. And we take this content and we port it over to augmented reality and virtual reality if that fits the educational imperative of what we're trying to achieve here. And one of the areas that we've been focused on most lately is symposium work. So it doesn't matter if it's a handful of learners in a room, up to hundreds of learners. And this could either be in person or virtual or even a hybrid event. And everyone's able to actively participate in either the sharing of clinical study information or go through a procedural workflow together and talk with a moderator or KOL about decision making or about the clinical study data to have a really rich and engaging dialogue in a consequence-free environment where everyone can participate and everyone can learn. It's no longer about just sitting back and watching a presentation or a didactic session. It's about actively participating and joining in that experience. And as I mentioned earlier, we also have a variety of apps that are available in the Google Play and the Apple App Store. I'd encourage anyone attending this event to join in and participate and experience it for yourself. We have a variety of different procedural areas, from airway to game focus on the gastroenterologist I demoed earlier, to CardioX focus for cardiologists, to pulmonologists, and our most recent app, Top Derm, which is played by dermatologists. And we could also take this content and, from a med school perspective or some other type of learning environment as a leave behind. So you might be learning about a specific procedure or a specific clinical study, and then there's the opportunity to learn more from it at your own free, during your free time, when it's most convenient to the learner, when they're on the bus, back home from the hospital, or at other time of their choosing. And everything that we do at Level X is all about scalability. So we can take, and this is an example of a spine experience that we created. We're working from, the image to my right to the left. We started from mobile and web. So this was a workflow where learners can start to use different tools on the spine on a mobile and web offering.
Hey,
and
Michael, sorry
Yes.
to interrupt. Just 30 seconds left, I'm afraid, sir.
Okay, sounds great. Thank you, Stuart. And we can then port that content over to VR, which the center example is an example of what we did with Oculus, where you have the entire setting, the clinical setting around you, and you can focus on the different steps of the procedure. And then augmented reality on the right-hand side with Magic Leap 2, which is used in the appropriate setting. And in wrapping up, we track all analytics at Level X, and so we're able to score, and we're grading, and we're really focused on the engagement part of this experience so that we can start to change and drive behaviors at scale and create the most immersive and dynamic experiences possible. I thank you all for your time. My contact information is up on the screen, and would be happy to engage in a dialogue if anyone is interested. Thank you, Stuart.
Thanks for that, Michael. That was really stimulating there. I got a question regarding interface and controllers, right? And where I'm going with this is, I recently, after a hiatus from video gaming for years, I thought, right, I'll get a PS5 and see how advanced it is, and wow, it blew me away. I'm currently stuck on Ragnarok though, right? God of War, there's one episode, one little area, I'm fighting a dragon demon, can't get over him, and I know the only way I'm going to get it is if I master the controls, and I got that dexterity. So, do you think this is going in an era whereby a physician or a surgeon could be at home with almost like a replica of a DaVinci robot control system, and they could be at their home playing essentially surgical skills on their TV sets? Is that where this is kind of going?
Absolutely. So Stuart, I really appreciate you bringing up that question. We're actively working on a project right now where it is a physical controller that is controlling a robotic system, and the learner is able to use their iPad in order to drive through the procedure and experience the software as well as the functionality of the controller and get familiar and create that mental model before they use the controller in another educational modality. So the future that you just mentioned is here, and we're actively working on it as we speak.
Fantastic. Well, I'll be more than happy to test drive it for you guys. So on that note, sure. Thank you very much, Mike. I do appreciate your participation in the show, and I will be in touch soon.
Sounds great. Thank you, everyone. Okay, and moving on to, I believe it's actually our last final live session or presentation. We have Baena Fahim. He's a representative of Mediview, and he's going to talk about how XR unlocks the full potential of standard of care imaging and navigation, peering through a new aperture. Baena, pleasure to have you on the show. Over to you.
Yeah, thank you, Dr. Corr, and the entire Houston Methodist team. Really appreciate the opportunity to be with you all today and the opportunity to share what Mediview is doing really in this new age of medical imaging and navigation. It's a really exciting time to be doing what this space is doing, because for the first time in a long time, we believe that technology has reached a point where we can finally unlock the full potential of the tools that clinicians have access to do their jobs. And that's what we're here to share with you today as Mediview. So my name is Baena Fahim. I have the pleasure of serving as CEO and president of Mediview. Just for context, we're about a 30-person company that just got through 510K clearance of our surgical navigation system that leverages extended reality. So I'm going to share my screen here and just want to make sure that everyone can see it. Is that coming through okay, Dr. Corr?
There you go. Perfect. Thank you.
All right. So, if you forget everything else that I say, please remember this one thing. This image represents how MediView truly unlocks the full potential of standard of care imaging to really simplify procedures by equipping clinicians with superhuman vision. So what is it that you see on the screen here? If you haven't worn one of these head-mounted displays before, you'll see that the two clinicians are wearing augmented reality headsets, and they're seeing digital information superimposed on their physical world. And fundamentally, they have a heads-up display of live medical imaging. They have full 3D superhuman vision to see the anatomy underneath the skin of the patient. And they can also see where their instrument is in the planning and the execution phase of a procedure. And when you really think about what MediView exists to do, we're really here to help simplify, democratize, and inform healthcare delivery. It really traces to trying to equip our partners and clinicians with key tools like visualization, collaboration, and insights that empower them to focus on what matters most, which is the patient on the table. So obviously throughout today, we've heard some really interesting perspectives on the use of robotics and visualization, and this space is really growing at an exciting rate and pace. A lot's being done in the education space, in the training space, in the preoperative space, and we're really championing and really hoping everyone in this space grows and wins together. MediView is focused on the intraoperative space for surgical navigation and intraoperative use. The way we look to build out the capabilities of standard of care imaging are really in three ways. We want to advance care delivery by giving clinicians an intuitive way of understanding what they're looking at. Give them the ability to collaborate, whether it's with a peer clinician or maybe an industry partner who's somewhere else in the country or the world, to help diagnose a problem with the system, help guide a interpretation of what the device is telling them. Or in the long term, leverage evidence-based data insights to inform predictive and prescriptive analytics. So this perspective that we've created a new coordinate space that brings together imaging, that brings together the device in an intuitive way, gives us the potential to unlock the full power of standard of care imaging that's trapped on 2D images today, but carries so much more potential with it. And really, the limitation causes this fundamental problem where the poor visualization leads to a lack of confidence trying to go from skin surface to target. And clinicians are very skilled, very well trained, and have this inherent ability to learn how to do things with training and more procedures. But as one of our, Dr. Kendrick at Mayo Clinic, one of our partners said, hey, I get in my plane and I have situational awareness that basically is helping me take off safely, navigate safely, and land safely. Why don't I have a visualization capability to plan, execute, and perform my procedures in an intuitive way? And this fundamental limitation ultimately leads to barriers that hinder patient care to less invasive procedures. And, one thing just from the empathy for our user, I didn't know this before I was at MediView, but medical imaging, work-related musculoskeletal disorder accounts for $120 billion of economic impact in this country every year. And the ergonomics of imaging and where doctors and clinicians have to look in order to access their imaging causes neck pain, back pain, hip pain. And we're really excited this upcoming RSNA. We've just completed a study where we'll actually announce some of the results from a meaningful study that shows how augmented reality can make a marked difference in improving clinician ergonomics. And the way we're thinking about it is alleviate clinician pain for patient gain. And it's really something that we're seeing is not theory, but actually playing out in the real world. So we really look to improve the visualization, improve the ergonomics, improve the collaboration by unlocking the full potential of the tools and imaging modalities that clinicians trust and have confidence in today. So what does MediView look like? This is through the perspective here of someone. Our target device today is the HoloLens 2. We've done some interesting work with Magic Leap as well as some other headsets. But this is through the perspective of a HoloLens 2 of our 510K cleared navigation system. So we are the first solution that really brings live medical imaging into the XR space to be used for real-time soft tissue XR imaging and navigation. So what MediView does is we take the standard of care CT, we segment it, we reconstruct it as a 3D volume, and then have a proprietary way by which we can present that imaging data underneath the skin of the patient in real time. So you get the intuitive visualization from the 3D volume that can come from a CT or an MRI or a cone beam CT. And I'm going to pause here just to show a point. The other part we bring in is live imaging. And the reason MediView looked at bringing live imaging into the XR space is that it's a known quantity. Things like ultrasound, fluoroscopy. These are standard of care approaches to understanding where is my device relative to my anatomy in the guidance during image-guided procedures. With the MediView platform, the real-time ultrasound is fused to the 3D XR visualization that you're seeing, while also being able to see the instrument in a planning, pre-puncture, and puncture state of the actual procedure. So the MediView technology looks at unlocking the full potential of both 3D imaging as well as live imaging and guiding instruments to targets in a much more intuitive capability, while also connecting clinicians across distances. This idea of being together is taking on a whole different meaning, even if you're not in the same physical space together. This truly is a platform that is meant to serve multiple clinical specialties based on their clinical unmet needs. Whether it's the ergonomics in ultrasound, whether it's the needle puncture during a biopsy, whether it's positioning during an ablation. We also are very cognizant of the resource limitations that exist in hospital systems today. So what if you could upskill and repurpose some of the staff and give the clinician full autonomous control of their entire system by controlling their equipment from an XR environment? And we layer these capabilities into different modules and bundles to serve different customers based on their needs, enabled by MediView's capabilities. XR really represents an opportunity where the entire ecosystem has an opportunity to win. From the clinicians doing their job to the patients who actually in the preoperative phase during consent, there's been studies shown that when they're shown an XR walkthrough, their level of anxiety and stress actually comes down because they understand disease state and what's about to happen during their procedure much better. We see what groups like Dr. Mark Griswold at Case Western is doing with Illumis in medical education. We look at the opportunities for reimbursement and reducing lifetime cost of care to the patient, where this truly becomes a benefit to the entire ecosystem. And here's some of the ways we're starting to see the MediView application make an impact in enabling less invasive procedures, increasing resource efficiency, and expanding patient access. We're seeing a shift, a great is, for example, in the world of cancer care, from open surgery to less invasive surgery. We see a lot of ASCs and OBLs opening up. We see this opportunity to say, you can take your scan to the OBL without having to have a live CT there. There's opportunities to enable more practitioners to perform at the top of their practice, whether they are MDs, APPs, or MPs, which then enables a greater resource pool to actually be able to deliver care. This isn't science fiction. This is really happening today. And just want to really thank a number of our partners on the clinical side at Mayo Clinic, Cleveland Clinic, Ohio State University, and others for really being some of the early adopter sites of XR and MediView technology. But very humbly, we understand that this takes an ecosystem and partnerships to really grow. And we have an active partnership with GE Healthcare that gives us access to that standard of care imaging at the byte level of the data in order to actually do what MediView does to unlock the full potential of that imaging technology. We've had a great partner in Microsoft on the head-mounted display side, where we're building solutions with them, evangelizing what's possible, and really wanting to tell the story of why clinical XR and why now. This has been an incredible journey with various partners. We continue to grow on the strategic side. This is an area where we're partnering very closely with the FDA through some of our recent FDA 510K clearance, our registrations, helping build out different venues and avenues to educate on the regulatory, the clinical, the technology side, and really bring that whole story of how do the various stakeholders need to partner to bring this space to life. We really are at a unique inflection point. We're building this ecosystem. We as an industry need to be accountable and support our customers and you who are utilizing the solution day in and day out for the adoption of this technology to really stick. Just to skip a little bit down, I really wouldn't be a complete discussion today without recognizing our team. A shout out to the entire both internal MediView team as well as our external partners. It takes a village to really accomplish something as groundbreaking as bringing XR into the OR. And I just want to say thank you to everyone that's dedicated countless hours, whether it's our team, our clinician partners, our industry partners, who are really helping bring this to market, because it takes that intersection of startup, big imaging, clinicians, regulatory to do this. These are our active areas of growth where we're really focusing to really continue driving the adoption of clinical XR. We need, as a space, to quantify value. We got to show whether it's the shift in site of service, the efficiency of a procedure, potentially reducing adverse events. This is an area where the space and MediView needs to focus on quantifying value, because we're introducing a very new way of looking at using imaging and navigation. Even though we just got through our 510K, we as a company continue to be focused on improving the workflow of the image processing, going from scan to hologram in very little time, expanding utilization outside of the US, because for this to become part of gold standard and standard of care application, it must expand beyond the US and other areas. And that's an area that we're focused on in the coming years. Like I talked about, partnerships. If you haven't seen it yet, we're about to launch a solution with GE Healthcare in the US for the interventional suite that allows clinicians ergonomic heads-up display, intuitive 3D visualization, and that remote collaboration capability at the point of care from a first-person perspective. And then we have our internal team, who is really boots on the ground, interfacing day-to-day with our current and potential customers, and maybe just as important is what we refer to as customer and user success. being there with our users to help understand the technology, train on the solutions, and support them in the intraoperative use of clinical XR. So we think about this as demonstrate value, continue driving innovation, partner with external entities, and really drive adoption through utilization, deployments, and what we like to refer to stickiness, where this becomes part of the standard of care imaging and navigation solution that builds on standard of care technologies like ultrasound, fluoroscopy, CT that clinicians trust today. We're just unlocking its full potential.
Okay, Mina, thank you very much for that. We're almost out of time, but two very quick questions. So again, what is, with your 510K FDA approval, etc., what is your intended use?
Yeah, thanks, Dr. Corr. So we're very thankful to the FDA, the process that we went through the 510K process. It's for the indications for use are the intervention of ultrasound-guided procedures for anatomies that can be visualized under ultrasound and CT. So we're actually very fortunate that it actually is a space to say, if you can see anatomy under ultrasound and CT, you can actually use the MediView solution head to toe.
Got it. And last question is, and this kind of ties it all back to Nico's original presentation, is, are you finding that you're needing to team up with the likes of Verizon, et cetera, to offer that 5G like edge computing for like high data transmission bandwidth?
Yeah, you know, that's a very important consideration. I mean, to be very transparent, I'm actually at Verizon's campus today. That's where I'm sitting. And, you know, Dr. Corr, the roadmap of leveraging more advanced technologies like 5G, edge, and when you start getting into heavier data like 3D or 4D ultrasound, that can't be done on a headset, right? You've got to do some of that processing at the edge and then leverage the devices for what they're good at, which is really good visualization. What about applications where you've got a frontline worker who's rendering care to someone in a nursing home or the front lines from the DoD? How do you connect them back to a world expert at Houston Methodist, right? Making that connectivity reliable and low latency so they can see the patient, they can see the imaging from a first person perspective. We're not going to build that infrastructure as MediView, and that's where partners like Verizon can really help. So we see opportunities on the processing side as well as the connectivity side.
Got it. Well, again, Mina, sorry, thank you very much for your time today, and I do look forward to meeting you soon in person. Thank you.
Yeah, it's a pleasure. Thank you, Dr. Corr, for the opportunity. Nice to be with you all.
So we're about to go into our final session or event of the day. It is our pre-recording that we took a couple of weeks ago. I mean, as you may or may not have guessed, it can be quite hard pulling all these international players together, etc. So a few weeks ago, we had on site Richard Vincent from Fundamental Surgery. We had Molly Newsome from Biomed, and this session was all about the role of immersive VR training and advancing procedures and patient outcomes, and it was moderated by Dr. Alan Lumsden. So on that note, I just want to thank the audience for your attendance. I want to thank our guests. I really feel it was a very synergistic, kind of productive session, and I look forward to seeing you all next year. On that note, goodbye.
Hello, my name's Alan Lumsden. I'm the medical director for the Methodist DeBakey Heart and Vascular Center. And I'm joined with two guests today who will introduce shortly, but we're united by our interest in virtual reality. I also happen to be the medical director for MIghty, and a subcomponent of that is what we're really interested in called MIRRIN, the Methodist Institute for Robotics, Imaging and Navigation. And we really see virtual reality as a very important component for that, potentially for controlling robots, but also for the education that needs to occur around that. And so let me introduce you to the two guests who are in the studio today. And let me go, first of all, on my right, ladies first. Molly Newsome is the Associate Director for Innovative Educational Solutions at Abiomed. So welcome, Molly.
Thank you.
And on my left is Richard Vincent. He's the CEO and co-founder of Fundamental VR. So what brings us all here today? What brings us from the Abiomed side is that they have a product, Impella, which is a pump which is used to support the failing left heart. And it's a very, fairly complicated device. And so they identified a problem, and that is, how do we extend education and how do we bring our care providers up to speed in terms of doing this? And so, Molly, I think you found fundamental VR as a potential solution. And so that's really where we're going to start today. Let's start off. Tell us what we need to know about Impella so that everybody knows what Impella does, and then tell us what you've done from an educational standpoint. How on earth did you start thinking about VR as a solution for this, Molly?
Absolutely. So like you mentioned, the Impella is it's a microaxial blood pump that works to help the heart that's failing. So both the left and right ventricle. So we have a couple different versions of. So we have the Impella CP with Smart Assist, the Impella 5.5, and then the Impella RP with Smart Assist as well. And then we have new products obviously coming as well. So not that it's a challenging device, but it's got its niche. So there's people that you want to be able to take care of patients over and over again to be able to be comfortable with it. So it's just one of those scarier devices that people use, and they want to have a little bit of practice with it.
Yeah, I mean, we think of these are not healthy patients. Okay,
They're not.
By and large, these are the sickest of the sick. And so the margin for error, and this has been a groundbreaking device. And so where is it that you see the need for education that VR can potentially fill a gap?
So it's interesting because we started it with, for physicians, and we were going to go with, how to insert it and do all of that. And we started talking with some physicians, and they made it clear to us that the problem doesn't lie with them placing the pump. They've got that down. They're not comfortable sending a patient to the ICU because there's so much nursing turnover, especially since the pandemic. So the nurses are straight out of nursing school or being pulled from a med surge floor and never taking care of an Impella patient. So they wanted an opportunity to have those nurses trained better so that they are comfortable sending their patients there and knowing that they're going to be cared for appropriately.
So that's the need. How did you link up with Fundamental?
Long story. We met with a couple different companies, and ultimately Fundamental was able to meet our needs. They've been great to work with, but they've listened. They work with our needs and have been able to put together a pretty great product.
All right. So, Richard, when a company comes to you and said, "Hey, here's the problem," how do you build your understanding of the problem, and then how do you build the model itself in terms of, talk us through the process of, here's the problem, now I'm going to build a VR solution.
Yeah, so there's a number of different elements to that, obviously. The first one is making sure that we get medically very, very keyed into both the application but also the educational challenges. With all devices in all different areas, there's a lot of different steps, but the key thing is where can you really have impact? Where are the real inflection points in skills acquisition that's going to have an impact on the adoption and the use and the safe use of that with patients? So we have an approach which is where our medical team will work with the Abiomed team, with Molly and her team, to really deconstruct that process, those steps, those key elements, bringing in clinical experts to help to really guide that until we can isolate those key points that matter. And then from there, you go into, having built that understanding, you then go into a process of building the 3D assets, the dynamics that go with that, so the tissue dynamics, the patient anatomy dynamics, and then putting those together into a pretty sophisticated virtual reality environment that then allows you to do those different scenarios. Ultimately, repetition is what we need to get to. Safe repetition, to give people opportunities to try correct and incorrect placement and understand the consequences of that. And that's really what you can do with this virtual reality.
So let's go back to step one. Here's the clinical problem. So what do you start with? Do you put cameras in the ICU so that you can see how a normal nurse or PA interacts with it? How do you get that initial data?
Every source we can use, really. So absolutely, let's look at video content, let's look at case data, let's talk to those people who are doing it on an ongoing basis, let's engage with the medical leadership around what good and bad should look like. And then really bringing all those pieces together, you start to build up a really clear picture of what you're trying to achieve.
So I had the opportunity to go into your ICU setup with Impella. It was unbelievable. And I mean, honestly, it's probably the most fidelity of anything that I've seen. And I'm always fascinated, how do you know what that looks like?
We live in it every day. You know, it's what we do as a business. We only spend our time within these environments to really understand the different constructions and organization of that, so that we can give that, as you say, high fidelity. It's great to hear your feedback on that high fidelity impression of what it's like to be there. You know, what virtual reality can do for people is to give you that sense of presence. Mm-hmm. And once we can convince you you're there, then we can really start to do the learning. And that's what we can do with this.
Have you ever seen the plank?
Yes, absolutely.
The plank. You talk about the sense of being in an environment. It comes part of Oculus Quest. You can download it. And you in an elevator, you go up to the 60th floor, the elevator doors open, and there's a plank which sticks straight out. You're 60 floors up. Now, you know that you're in your living room, and there are people who just cannot even step on that plank. And so it does bring the sense of reality. And so, okay, so we created the environment. Now what about the scenarios? So you make a list of the scenarios and troubleshooting and things like that, and you give them,
Yeah, so we look at some of our common themes that come in for our call center, why nurses call the most frequent. We collect all that data, so we look at that, and then we just kind of prioritize them based off of that. So we're able to, suction, or if the pump is in the wrong position, if there were purge issues, we're able to go through kind of step by step with those, and we work very closely with the fundamental team. They probably know our pump as well as we do at this point.
So do you allow them to make mistakes in these environments? You kind of alluded to it a little bit. Can I really screw it up?
Yeah, absolutely. I mean, with any system, it's constrained by the programming scenarios you put into it. But absolutely, we want to build in scenarios where you have the opportunity to have error and see the consequences of that. When you walk in to a cath lab, you don't know what you're facing in the real world, and ultimately that's where we're trying to get to with Molly.
Very good, very good. So, how are you going to deploy this? You've got it.
We got it.
As you were pitching this internally, I'm sure everybody didn't go, "Hey, this is a great idea. Go spend whatever it is you have to spend on it." I'm sure there was resistance to it.
Sure.
How did you get to overcome those barriers?
I think the pandemic helped. We needed some sort of resource that did not require in-person training. And it also allows us to have multiple people in one space from anywhere in the world. They can all be at different places and all meet and collaborate into that one space. So that gave us the opportunity to kind of work, apart but together in the same space.
So when you say people can come in from any part of the world, you could be a proctor, and you can teleport into my environment.
Correct.
Through those headsets. I will see you. You're an expert maybe in California, wherever your headquarters are, and they can talk to me in that environment.
Exactly. We can, hand off our ultrasound probe to the other person, and we tend to, everybody likes to high five in the environment and give the thumbs up, but yeah, we can all be in the same space.
And so obviously you sold it pretty well inside Abiomed. What's the feedback from your colleagues now that you've created something?
It's definitely cool. There's no question. It's definitely got the wow factor, the cool factor. Now it's time to start implementing it to our customers, the whole reason we got it. So
you jumped onto one of the questions I had is, it's always cool. And I'm sure you hear this all the time, probably drives you crazy.
Yep.
Because it's got to go from the cool factor to the validation factor. Everybody's going to do it once. That's my experience, is that how do you make sure that they're going to do it again and again and again, which is going to give the sustainability? You probably thought about this more than anybody.
Yeah, for sure. I don't know more than anybody, but certainly we give it a lot of thought. I think validating the efficacy is obviously a key point.
Okay. But how are we going to do that? That's obviously...
So you're going to do it versus other methods of education, and look at it versus those and say, well, actually, does it achieve a better outcome there? or the same outcome there at a lower cost, because then you can of course do more. So that's the first one. Second one, and ultimately you want to get it into a true patient outcome scenario where you start to validate it against real life. So what happens as a result of having people using this system? That we're on the journey towards. We're not there yet.
So a lot of the early stuff, this tells you where the money is in orthopedics.
It was, yeah.
Have they done any of this validation yet?
Yeah, we've done it ourselves at Fundamental. It's been done across a number of other companies as well. And you see some great results, and so with us, with our platform, we kind of have two different parts to it. We have a kind of standalone VR, the traditional headset with controllers, and then we have a haptic VR where you have haptic engines that deliver the sense of touch. So there's been validation done on the standalone systems, and what you see there against traditional training is anywhere between a 60 and a 150% increase in the speed of knowledge acquisition, which is a great start point. On the haptic side, what we've seen there, and this is
when you say haptic, describe what you mean.
So what I mean there is the immersion that you get with virtual reality, but now you're holding some grounded haptic engines. So these would be a small droid-looking thing.
So you can feel.
So that you can feel. You have resistance, you have force feedback, you can feel flow, you can feel weight. All those things that are important when you're actually interacting with a patient. So there, what we found on top of the advantage of VR, haptic VR gives you about another 40% increase, but this time we're talking about skills acquisition now, so the speed of acquiring skills. Ultimately, in the medical device space, into your space, the speed of acquisition of knowledge is the driver towards impact on patients, because the sooner you can get people trained and confident and capable, obviously the better the outcome is going to be. So that speed is a real key factor.
So I get when you're building a room, you take a picture of the room, whatever it's you build. How do you measure what the forces you need in haptic feedback? I mean, if you ask me how much pressure I put in a needle, I have no idea. I don't even know where to start in thinking about it. Do you measure those?
So we do. But actually, so it's how you feel as opposed to the pressure you apply. So whilst we could say, okay, there's 2 newtons being applied here to this particular element, that's not what you feel. So we have to kind of get a measure on the feeling of it. So the process we have for that is we have a calibration system that we bring in experts and say, how do you feel it? How do you feel it? And we aggregate that knowledge. And then once we've got it, we lock it, and then it's there within the platform, and we can then call on it each time.
Very good. Okay, Molly, so you've got a nice environment. What are you going to do?
So there's twofold. Number one, our reason for it is for the ICU nurses and to get them using it repetitively to get them comfortable so they can make those mistakes, in the virtual environment versus in a live patient environment. And then we're also working on our new hires. So the staff that's coming in that's new to Abiomed, it gives them the opportunity. And like Richard mentioned, the speed of learning. So the sooner we can get them trained, the less money it's going to cost us as well to get them, to have them in-house and out of the field. And we want to be able to get them certified sooner. So the repetition of that would allow for that.
So the only other cardiovascular company that I'm aware of that's built anything like this is Endologics, which is a stent graft company out of Irvine, California. And it's remarkably good in terms of, there's no haptic feedback in it, but in terms of sequencing the procedure. So it's been slow in the cardiovascular world. Is there any reason why we're behind we're certainly behind orthopedics. I'm not sure we're behind the curve, but we're certainly behind where orthopedics is.
Your observation's right. I mean, certainly orthopedics was the first point at which VR started to develop. I mean, we've seen it now move across lots of areas, this being one of them, robotics, ophthalmology, urology, other areas. And I think the build-up there has just been a little bit slower. I'm not sure why that is particularly, but I know that there's a lot in development at the moment across not just our company, but a number of others. So I think over the next 6-12 months, we're going to see quite a lot hitting the market, which is great, because the more of these applications we can get out there, the better the outcome.
Yeah, my sense when you talk to device companies, they're all interested. I'm sure they're all talking to you, but nobody's really completely committed. You're one of the first ones to commit and say, hey, this is what we're going to do. I guess that's why you're in charge of innovative education. Again, from your point of view, obviously this is fundamental for fundamental. It's how do you get them from Yeah, they're hedging their bets. They don't want to be left on the shelf if the other guys basically suddenly knock it out of the park. But they're not really there and sticking millions of dollars into this. Well, how do we get them there?
So, in our industry, everyone wants to innovate, but not necessarily go first. So I think the more you see use cases out and the more you see validation and we see feedback from clinicians on the use and the efficacy of that, the faster it starts to move. We've certainly seen this go over the last 3 years from kind of interesting innovation projects to now scale deployment. And we're seeing a number of companies, again, across different sectors, using this at scale for the first time. But it's happening in real time. This is an industry that wasn't around 8 years ago. Yeah. When we started, everyone's like, what's VR? Yeah. Today, now we've crossed that bridge. I think now it's about just slow development out.
So yeah, I may have crossed that bridge, but there's total confusion out there. And you're probably the guy to VR, AR, mixed reality. What's the difference? Tell me what these different things actually happen to be. And you're in the VR space at the moment. Are you looking to move in? First of all, describe to the audience what these are.
Okay. So really simple. The way I think about it is AR, I'm looking through a device at the real world and something's being placed onto it. So it could be my phone. So it's that becomes my viewer. Mixed reality, I'm wearing something on my head that allows me to see the real world with something overlaid onto it.
Cameras on it.
Cameras on it.
Essentially relay the picture.
But I'm seeing you, but we've now got the patient here to my left. Virtual reality, we take control of everything and give you full immersion into that. And all three have their place. I think for the use cases for the training that we're doing, virtual reality is a more appropriate one because we want to control all of those inputs. I don't want someone walking across your line of sight whilst you're in the middle of an operation or a procedure and you go, oh, hello, John, how are you? Kind of that. I don't want that. It wouldn't happen in the real world. Yeah. So it doesn't need to happen here as well.
Might.
Okay, well, it might, yeah. But hopefully it doesn't happen too often in the real world. So it's those three different areas. I know they all have great use cases, but the world of immersive tech, which is really the way we define this, what we found is for most of and our customers have found for most of the use cases that they're currently addressing, virtual reality works more effectively. There's a lot of intraoperative work coming through in mixed reality, and that's really interesting. Right. But fidelity needs to improve a bit more. Some of the capabilities of those headsets needs to improve as well.
So the VR headsets are obviously cheaper. Is it cheaper to build the environment, or does it really not matter which headset you're working with?
Good question. So I don't think it really makes any difference, to be honest, in terms of the device it ends up on. There's more to build in virtual reality because we have to take the entire environment. The counterpoint to that is if you want to train within a cath lab with mixed reality, you've got to put someone in that cath lab, and that comes with a cost, right? Whereas in virtual reality, we create it once and you can use it infinite times. So ultimately, I would say it's still probably more cost effective in virtual reality.
Very good. So obviously reps can make or break great training ideas whether they buy into it or not. Have you shown this? How many people in Abiomed have seen this? So an opportunity.
Yeah, so we've trained all of our regional clinical managers to go out and use it with customers. The problem I'm running into is we've never done anything like this before, so we don't know the right way to train people and how to use it. So we have them out kind of using it in different scenarios and for different reasons to determine what that should be. So that's where we're at right now, is we're out and gathering feedback. So every nurse that goes into that space, they leave us feedback afterwards. How did you feel before you went into the environment with Impella? What was your comfort level? Now that you're out of the environment, how do you feel? So we're looking at that and measuring that.
So you're collecting data.
Correct.
That's going to be very important.
Yes. So just basic surveys to see how they feel before versus after, and then just getting some feedback. How can we make it better? What would make this more realistic? What do you need for this environment?
And so you both chose Oculus as the what is it now, Meta? I guess I should be saying. What's the headset that you've chosen, and why did you choose that?
Well, so there's a lot of great headsets out there. The Meta devices, Meta 2, Meta 3 that's coming through, and the Meta Pro, they're great. They are great devices, and I think at the moment probably at the forefront of the hardware. But we're hardware agnostic, and deliberately so, because that changes. And what we don't want is Molly to make this significant investment, have the team start to understand and start to use it with their customers, and then find that the headset hardware lets them down. So the ability to port from where it currently sits into a new device, which might be from an HTC, an Apple, a Microsoft, or another player who's yet to present themselves. That's important for us. So the software sits independent of the hardware.
So you'll see this is a glowing apple in the back. Oh, actually, it doesn't glow anymore. I'm an Apple guy. I got to ask you about the Vision Pro and where you think this is going to be.
I think it's great. There's no, for the industry, there's no negative to Apple being in the market and coming through. It's been a long time coming, so we're delighted to see it happen. The device itself looks fantastic. You won't be surprised here. Our R&D guys are working with the SDKs at the moment to understand its use and how we might.
Did you get your hands on it early because of who you are? I mean, they're looking for early partners apparently to roll it out. And do you have one?
We don't have one all the time at the moment, but we do have access to it through Apple. Are very supportive of the developer community, so we've been able to see how that will work, and we could use it going forward. It's great. It's got its limitations. It's more focused on mixed reality at the moment.
But it can do both, can it?
But it can do full immersion as well. Yeah. So that's really exciting.
The difference between $300 and $4,500.
Oh wow.
It's
honestly, it's interesting. One of the reasons we were interested in Oculus is, so for example, we run this thing called Boot Camp, and we essentially have 50 vascular fellows coming down here. You can almost buy them the Oculus and load it up with whatever you want loaded on there. Save the expense of a flight, save the expense of hotel rooms, and so it was very cost effective. And you can potentially brand these; they'll brand them with your logos, for example, and your content. And so it seems you obviously did the cost analysis of this and thought this was an effective way to go.
Yeah, and we were using very large simulators where there were two big crates of things that had to be shipped, and then you put that together.
They're expensive.
Very expensive.
It's like $10,000 to ship these things.
It's a lot.
We just ask for them. We have no idea how much it costs, and expected to ship them in, kind of thing.
Exactly. So using a headset to be sent out is a pretty much reduced cost.
You gonna ask them to send them back, or you gonna let them keep them?
Right now, our clinical managers have them, and that those are theirs, so they're keeping them. And then we're going to be kind of doing a loan out program where if they want to take more, they can have them, and then they'll send them back afterwards.
So you've got at least 3 different clinical stuff. We'll get to the haptic feedback and the access in a minute, but you've built not just an ICU, and tell us what else you've built and why.
So we've got the ICU, and then we've also created a transport environment. So one of the areas that we know that we need more education is those that are transporting patients from hospital A to hospital B while on Impella support. It's a pretty critical time with a pretty critically ill patient. So we've developed a helicopter environment where the patient is on the stretcher in there. It's a very tight environment. So
because you have to get down low.
Yep, you've got to be sitting down.
Bang your head when you're
awesome environment.
Oh, it's really
cool.
Good. Yeah.
It's got the sounds, so it sounds like you're in there. The clouds are moving next to you, so it's a pretty cool environment. But it brings it into, again, the realism of being in this small confined space that they truly are in to have to manage a patient.
That's really good.
Yeah.
What? Anything else you're going to build?
Well, the haptics.
What do we need to know that you don't want to tell us about?
The haptics we are working on, that is, we have 2 parts that we're working on currently, which is ultrasound guided access. We know that, with a larger bore access with Impella, outcomes are detrimental to good access. So we really want to make sure that those best practices of using ultrasound with micropuncture is done. And so when we train people who are early on in their fellowship, again, it gives them that tactile feel. So they can hold the ultrasound probe with one hand, they've got the needle in the other, and they can actually feel as it's going through the skin and as it punctures the artery. Same thing with dilating it up with multiple dilators, putting the sheath in. And then the second part of our haptics is doing axillary cut down, putting the graft on to be able to insert Impella from the axillary artery. specifically our Impella 5.5.
So I've not seen the surgical part yet. So just FYI, ultrasound guided micropuncture access. If you need the scenario, that's all up on our YouTube channel. We've got non-edited yet, cut down in access to put, when they put 10 million background graft onto the axillary aorta. All righty, sounds like going to keep you busy.
Absolutely, yeah. It's a great programming. I mean, Molly and Abiomed have really, lent into this and can see, I think, the benefits of the early work that's been done. And so it's great to see the stack going through, and to see the haptic systems coming through now. For us, that's when when you literally get hands-on. It's when you start to really.
So let me set the scenario a little bit for that. Is that it's a little controversial. Okay, so think of surgical robots, for intuitive surgical. Okay, big criticism was no haptic feedback. Now, in a situation you think it'd be critical.
Yep.
But things have changed. They have surrogates. You still don't have haptic feedback, but there are surrogates for that. Tissue stretching thing. Surgeons will learn to work without haptic feedback. How important do you think it's going to be in the VR environment?
I think it's essential. Okay. Simple as that. If haptics are important in the real world, like the sense of touch is important in the real world, then it matters. If obviously in the real world you're using a robot that has no haptics, well, then you don't need to learn that sense. I would argue, though, that even with intuitive, you don't have haptics of patient interaction, but you have resistance within those. So actually you are feeling something, and you need to learn how that feels. So I think they're essential for most use cases when you're into true procedural training. Obviously, if you're in technical training, you're in more knowledge acquisition, then less important at that point. We can do a great job without them. The ability to just turn them on when you need them, though, I think it's fantastic.
So the one prior to using the ultrasound guided access, the ones that I'd seen were knee replacement, hip replacement, where you had the virtual hand became the hammer or the drill, and it was pretty impressive. Not that I've ever actually done it.
Yep.
And so the drivers for doing this, okay, you build the environments, but I don't even know what you call them, but whatever gives you the haptic feedback, are they off the shelf? No?
No. So we've spent the last 5-6 years building what we call a haptic intelligence engine, which is basically it's 5 or 6 years of clinical and technical development. So what does it feel like? Please tell us and show us, and then let's codify and lock that so that we can build up a big library of those capabilities. That's what we've been working on for a long, long time. The physics calculations around touch are really complex. It's the most complicated part of what we do. It's the most exciting part too, because when you get it right and you suddenly go, oh my goodness, that does feel like the real world. You felt it. It's amazing. You felt it. It really, really makes a difference. So it's the bit I'm excited about.
Yeah, essentially, we were talking a little bit about Corindus as an endovascular robotic company, and one of the things that they had done, which really fascinated me, is they basically you navigate a guide wire across some stenoses in a blood vessel, and they'd set a whole series of experts down, and they had all these sensors attached to the bottom to your hand and the bottom of the wire, and behind you, all these graphics were measuring exactly what you did. And part of this idea was to identify how an expert handled the guide wire and could they pre-program the robot. And so I guess it's kind of a similar concept in terms of how you're measuring the fidelity of pressure, rotation, whatever it is basically on your hand.
Yeah, absolutely. Yep. And when you have that in place, you start to analyze the data that comes out of it. It's quite interesting. So you'll know this from your extensive experience. So if I was to pick up a scalpel and make an incision, the movements I would make and the hesitations would be very different to yours. And with the haptic systems, we can measure that, and we can therefore interpret it and then start to predict as well. So based on my movements, my hesitation, the way I draw that scalpel, my system would say I'm nowhere near good enough to be doing that in the real world.
So will you be able to guide that?
Yeah.
That's very interesting. I
never
thought about that before.
Expert tuition through AI. That's our data teams are working on that right now. Yeah, it's not been implemented, but it's part of where it's going now.
Very interesting.
So just as with the VR system, we can check where you're looking, where your eyes are pointing, what you're doing, the decisions you're making. Bring in the haptic piece, you get another dimension to understanding, and that's ultimately what it's about. Again, back with your system in the real world, you measure and record everything that's going on with that patient, so that if you start to get an adverse effect, you can rewind that data, right? Well, we can do it in the virtual space. It ties up really well.
Even in the haptics, it's measuring the angle of insertion. You know, we don't want them to insert the needle at 60 degrees. And so it'll actually come up and say, you know, you failed this portion. This is the correct angle you should be at. So it actually measures that.
How do you get the ultrasound? You capture the ultrasound and then you build your own ultrasound images?
Yeah, imaging generally in virtual reality, you know, we've done a lot of work in building this through. So we have a virtual ultrasound system. Yeah, so we take 3D anatomy that's within the virtual reality system that we've built, and then we apply the virtual ultrasound to it, and it displays as you would expect to see it in the real world with the real systems.
Very interesting. There's a guy in town called Bruce Blouse, and he runs Blouse and Medical Animations that we actually built patient-specific animation. And part of that was we recorded the video, so they had this sequence of the procedures. We can also scan devices. And so we built this big medical library of scan devices. Companies would not give us their CAD drawing. So but we don't need it. We can actually stick them in a CAT scanner, take a picture, and give you a model of the device. And it was very interesting because it saved their animators time. They were importing that into AutoCAD, I think was what they were using. And so this stuff's really expensive. And when you go and, I presume if you visited Fundamental, there's going to be rooms full of smart people working on computers.
Correct. Yeah.
And so how can you shorten are there things that we can capture up front? Like, for example, let's say we scan the Impella device. I think we have scanned the Impella. If we were to give you that 3D construct in whatever format you need it, the things like that help you?
They do.
They
do. It depends on how it's been created and scanned. But yes, absolutely. If you can start with an asset and then start to develop from there, so much the better.
So this was the project with Siemens, and the Siemens project was we wanted to build a 3D medical device image library, and they gave us it back. They said, we don't know what to do with it. And part of this idea was that here's the device. It started off really with this project. If we give you an image of a heart valve, can you basically does it help your rendering whatever you're doing of that device? Then I've kind of morphed from there into automatic identification of devices on a CAT scan. Yeah, this is the device. And then, of course, go beyond that is, now it's broken. So IVC filters break, for example. Here's the filter. This is what it should look like. Here's what it's not. So I think there's an opportunity for the clinical imaging to help short circuit, because we're going to have to make it faster, cheaper. And so thoughts on that?
Yeah, absolutely. We constantly look for ways to find really good, high quality, three-dimensional objects that we can use reliably. If you look at the anatomy, aside from the device itself, you look at the anatomy, just making sure that is perfect is the key thing. So there's a lot of models that have been created. Sadly, a lot of them aren't quite perfect, and we need to start with something that is pin sharp, accurate to the human, and then we start to obviously create the pathologies and such like that we need to have for the particular use case. When you look at devices, absolutely, if there's a way to move faster with that, we absolutely do. We use a few market available machine learning systems to, again, help with some of the creation there to try and speed that up. But ultimately, there's a process, we call it rigging. So, we need to rig the model so that it will dynamically do the things we need it to do, so that we know if you're making insertion, it will rupture or it will move or adjust in the way that you would want it to for the training objective. Again, sometimes the models that are available off the shelf don't give you that capability. So we actually have to take it and then rebuild it to achieve that.
Off the shelf. You can go to another third-party vendor and say, I want a model of aorta or the heart or something like that, and you take it and use it and modify it.
So we don't do that very often because most of it isn't at the standard that we would need. But there are lots of people who've been making lots of models, yourself included, for a long time. So if it's there and it's available and it's useful and it speeds up the process and lowers the cost, then I'm all for that.
All right. So what's next? You're going to roll this out, get a bunch of feedback. Let's say it does great. What are the opportunities going forward?
Well, we have a lot still to build, more scenarios. have them in an environment where not knowing what's going to happen next and the unpredictability of being in the ICU, having them follow through with different scenarios that happen, building out the haptics, eventually getting into the insertion part. So, you don't push a guide wire when you feel the resistance, and being able to build that into our haptics kit as well. And then, our other devices, we've got the Impella RP, which we haven't even done anything with yet, the right-sided device. So right now we're focusing on the Impella CP in the ICU. We've got the Impella 5.5 for the axillary insertion. And then we also want to start working on the insertion of the Impella the Impella RP.
So when you choose the people you're going to give this to, have they all had experience in VR? I mean, you're really fighting two battles here. Number one is putting somebody in an Oculus for the first time. They never get it right, and so you got to get over that hurdle to be able to really validate this. And so, are the people you're giving this to got any kind of experience in VR beforehand, or you having to train them completely from scratch?
Both, and it's actually one of the survey questions we have is asking them if they've been in VR before, and if so, was it for medical, was it for gaming? What reason were you in VR?
Maybe you don't want to know.
Or that. So we've had a lot of feedback where some people would even say, I'm 60 years old, I've never been in VR, but this was amazing. Yeah. So there is a learning curve to it for sure, but it seems that the people are getting it, and I'm sure that as we continue to move on, the technology is just going to get better, make it easier.
Yeah, that's what I always tell people is this is as bad as it's ever going to be, and it's pretty darn good. I mean, it is. I mean, this is the new world, and it's really pretty good. I can't even imagine what this is going to be like, 5 to 10 years from now. So that's your job to speculate on what is this going to be like.
So someone told me a long time ago, never try and predict the future because you'll get it wrong. But having said that, I will. I think I agree with you. The hardware today is amazing. But compared to what we'll have in 5-10 years' time, what happens with technology is it becomes transparent, it becomes invisible, and that will happen here.
That's a good point.
And so it will become less friction. There'll be less friction to it. It will become much more frictionless. You talked about the collaboration system. So the ability to pop on a headset and just be somewhere else. Well, it'll be in glasses the size that you're wearing in 5 years' time. Yeah. It will be in your eye in 10 years' time if you want it there. That's going to happen. The ability to go to mixed reality, to go to full virtual reality without wearing headsets, wearing gloves. And again, we're working with a number of manufacturers on haptic gloves so that we can bring those into the system. They're less than a year away now from commercial use. So it's moving really fast. And the only thing I know about all tech and all the technology realms that I've been in is that it always gets, Moore's law applies. It gets better faster. So we build to future capability and then degrade to what we have today. So in terms of fidelity, in terms of the models, because the processing power in the headsets today isn't as good as we'd want it to be. It's amazing compared to what it was 3 years ago. And in 3 years' time, it will be 10 times better.
I was one of these guys who bought Google Glass.
Me too.
Did you buy that? It's interesting because as mentioned, we work with NASA and some projects around pumps and pipes. And they actually took some of the astronauts, and they have a subsea environment down in the Keys, and they had a bike that they took down there, and all the instructions were in Google Glass. It drove them crazy. It was pretty hard. It was pretty hard to use Google Glass. So Oculus is a long, long way forward from that. So, in my glasses, elaborate a little bit on that. I don't know that I want it in my eye, but in my glasses, my surgical glasses that we use. For magnification, I could pull up a CAT scan or something like that, and them would be very valuable.
Yeah. So it's just about the journey of hardware and miniaturization. So already, the optic technology that sits in the Meta 2, the Quest Pro, the new HTC devices. That's 3-4 times as powerful as it was 2 years ago. The new Apple device we talked about earlier, again, the fidelity on each of those eyes is fantastic, and the size is much smaller. So getting it into your glasses is all about that miniaturization, and it's happening in real time. It's coming through.
Well, I'm out of questions. Then you want to ask me, or do you want to ask one another questions?
Yeah, so I'd love to know, in terms of the work that you're doing here, Dr. Lumsden, with the Mightyverse. Last year you were talking about the Mightyverse. Obviously, we've been supporting you on that a bit. How do you see that developing over the next couple of years with all the things that we've talked about?
So again, the story behind Mightyverse, and Stuart Corr is the guy who really put that together, was that the pandemic. I mean, really, there are obviously a lot of bad things that happened in the pandemic, but there were a remarkable spurring of interest in these kind of remote technologies. And we went, okay, we got this beautiful place called Mighty. Depends upon bringing people down there. It was basically shut down for 2.5 years with nobody coming in there. Yeah. And the question was, can we build, a Mighty, in VR? And that was the whole concept for this. In parallel, we built this process called DeBakey Education. So we got all of these videos. We got 2,500 videos, and close to 100,000 subscribers on our YouTube channel. So we have content that we can potentially showcase in that. It's not really designed for VR, but you can blend both. And then one of the things we started working on is, here's a case, extract the aorta or the aneurysm. Now you can handle this in the VR environment. So somebody can actually pick it up. They can be from, as you alluded to, anywhere in the world where they wanted to do this. And so that's all been created. Now we kind of need to start putting content in it, and we have to do what you're about to do, and that is test this, okay? It's not going to be without its challenges, but I think, I guess the challenge I always looked at is, it used to be you would come down here to have education, and we give you a lecture, and then we believe on hands-on training. Well, what Zoom, you don't need to travel anywhere for a lecture. We can deliver a lecture to you very effectively anywhere. You may not quite have this to and fro interaction that I still think is valuable. But so what we've been kind of focused on is exactly what you're talking about. What is it that you can create that mimics this hands-on environment that we think we excel in here? And that's kind of where we want to go with this.
Yeah, makes a lot of sense. And I guess, again, there's so much great educational content out there. And, some people subscribe to the metaverse idea and in whatever definition they want to choose for it. But the one thing that's clear with it is going to be over the next few years, how do you connect up those different spaces? So the Abiomed spaces, the Mightyverse space, etc. So starting to create universal access that allows you to move between them, with the right gating and such. I think that's going to be really interesting.
So that's a great question. That is that you're going to control this. So you put on the Oculus Quest. Do you have to go to the Oculus store to download this, or how do you get it into the headset? And then how are you going to control who has access to this? What do you get?
So it'll be in our headsets. So it won't be available in the store. So it'll be on that we would load them on there to the headsets we have. So
obviously you went through a thought process. Nothing in the industry is ever done by chance. It's always completely vetted. So what was the discussion around, hey, just put it up there? I mean, you can still password protect it so that you knew who was using it. You think you'll ever get to that?
Possibly.
That's a great answer. All right. Anything else you want to add?
No, I'm good. Thank you.
No, good on my side. Great conversation.
Great discussion.
Right. Well, thank you. Thank the team here for helping put this together. We really appreciate you coming down here to Methodist and allowing us to participate. Hope we're going to get a chance to get our PAs in your
you will.
environment.
You
Thank
will.
you. Thanks very much indeed.